I guess before my talk, you'll show me how to control some whatever, right? I just zoom in regularly.
Yes, so you will just press share screen.
Okay, okay, perfect.
In the window of the PDF, and you control it.
Okay, thanks. Thank you.
Yes. Andrei?
Yeah.
Could you please stop screen sharing so that Erez can start? And I will now share Erez slides.
Is it on?
Yes. Yes, it is on, and I just send it through chat to everyone so that
Thank you, Dima.
folks can scroll back if needed.
Okay, I'll be right back.
Our first speaker for today is Erez Lapid from the Weizmann Institute. And I can indeed see that he is in his office in the Institute now. He will tell us about results and conjectures about parabolic induction for the general linear group over a p-adic field.
Thank you very much, Dima, and it's a great pleasure and honor to speak here in this wonderful Zoom conference. Everything I will say about Joseph will be, by the way, is he online?
Yes, he is.
Okay. Everything I will say will be not sufficient, but let me just give a small anecdote that a few years ago, Bernstein was co-organizing some course or seminar with computer science people. And these computer scientists are no-nonsense people. They get millions of dollars for their patents, and one of the world-class computer scientists. So it was about linear codes and some aspects of it, and then one of the distinguished people asked him, "Are you talking about theoretical bounds or practical bounds?" And I was surprised from Joseph's answer. He was kind of taken aback and said, "Me, theory? Of course I'm interested in practical mathematics." So that's my small anecdote about Joseph. One of the fields that Joseph fathered, so to speak, is representation of p-adic groups, and among many other fields. And there is some tension in his papers between general groups and GLN. And I will talk about the GLN stuff, just like Sasha Braverman, but of course very different matters. The GLN theory, of course, after the pioneering works of Bernstein and Zelinsky, it had quite ramifications, and it's connected to many other disciplines in representation theory, which are unfortunately outside my purview and my comfort zone. And I will just apply many forgetful functors to all the things I don't understand, so please bear with me. And most of the things I will speak about, they are based on joint work with Alberto Minguez, who I believe is also in the audience. Can you hear me well, by the way, with this microphone? Okay. Okay, so without further ado, yeah, so I will now focus on the kind of the trivial part of Roma's talk from yesterday. So let's fix a non-Archimedean local field and consider finite length smooth representation of GLN, and consider all the GLNs together. And the most basic functor is parabolic induction, which is customarily denoted by pi1 times pi1. And I'm interested in, or we are interested in study irreducibility of this parabolic induction. And if possible, we would like to give criteria for this property. And by criteria, I mean, explicit criteria that you can go to the supermarket with, not, some equivalence of A infinity category or something of this sort. Okay, so the first order of business is a result of Hernandez, who proved it in another context, but you can transfer his proof to the GLN context and in the p-adic context. That was done recently by Max Gorevich, not related to Dima Gorevich, except he was his postdoc, and my colleague, my collaborator Minguez. Max is also my collaborator for other things. Anyways, so it reduces the question to k equals 2. So to test irreducibility, you just have to test each pair. Okay. So how do you test irreducibility? Well, it's not a trivial question, but one important tool are intertwining operators, which are very well known. And they are given by some integral formula, which converges for real S large and admits meromorphic continuation, in fact, to a rational function. And then you simply take the leading term in the Laurent series. It's never vanishing, but you take the leading term, and that gives you a non-zero intertwining operator. So I would know it by R pi1, pi2, it's a non-zero intertwining operator from pi1 times pi2 to pi2 times pi1, always defined. Don't worry about scalars. They're immaterial for this. And then there is a nice and surprisingly recent result, which I won't explain the motivation or their motivation, Kang, Kashiwara, Kim, and O. They are not p-adic people, but somehow, mathematics is connected. And they had a very nice observation. So in general, the category of representations is highly non-semi-simple. So Schur's lemma does not hold. However, for this particular representation, pi times pi, so now we will consider the case pi2 equals pi1. And in that case, the converse of Schur lemma holds. And in fact, it's enough to test this particular intertwining operator, whether or not it's a scalar. If it's a scalar, then it's irreducible. Of course, the converse is clear, but this is enough. And I would call this property square irreducible, not to be confused with square integrable, so I put it in a square. And okay, I will not get to this other context that they do it. And so we have some class of representations. And for instance, if pi1 and pi2 are square reducible and pi1 times pi2 is irreducible, then it is also square reducible. So in particular, if you have square reducible, you can multiply any number of times, it's still irreducible.
Erez, I'm sorry, I missed the original notation. So your induction, is it normalized induction or just?
Right, so I take the highest term, the leading term in the Laurent expansion of the intertwining operator.
No, I'm saying that when you write pi1 times pi2, this is induced representation.
Oh,
Are you using normalized induction or?
Yes, normalized induction. I think I said that, yes, okay. Right. Any other questions so far? Okay, so here are some basic properties, very classical properties. So maybe the most basic one is actually not to Bernstein or Zelevinsky, it's due to Olshansky, and it says that every irreducible Caspital representation is square irreducible. And in fact, his proof is valid for square integrable, so square integrable or square irreducible. It's valid for F Archimedean and non-commutative. Okay, and then there is the fundamental paper of Bernstein Zelevinsky. I think when I was in graduate student, it was one of the first serious papers that I studied. It made a huge influence on me, and as well as many others. And they classified when you have two Caspital representation, when the parabolic induction is irreducible. The answer, of course, is if they differ by determinant to the absolute value. And then, as Zelevinsky had an outgrowth of this paper, well, we will get back to it. And so, for instance, he proved that every irreducible generic or unramified representation is irreducible. And then, so this is kind of a part of the classification, consequence of classification. And then Bernstein had another method with these distributions, this famous paper that implies that every unitarizable irreducible representation is square irreducible.
I have a question. So how, like, the first statement is compatible with the second one?
I hope so. I mean, if there's no typo. So
if rho 1 is equal to rho 2 and they're both Caspital, the product should be reducible?
Irreducible.
Irreducible.
Yeah.
And here is reducible, I see.
Okay. So, yeah, I should point out, I think it's fair to say that the implication of Bernstein's distributional theorem to this fact is due to Jacquet. Okay, but anyways, it's a known and classical fact. So now we wonder whether there are any non-square reducible representation, and the answer is that there are, and the first one was given by Leclerc almost 20 years ago. I will get back to that. Okay, so what's the point of this square reducible guys? Well, so part of this KKKO paper, they have many, many things. I'm just kind of scratching the surface. So they show another very nice fact. So start with a square irreducible guy and start with any other irreducible, square irreducible or not. Then they show that the socle of pi times sigma, can switch the roles also, is irreducible and occurs with multiplicity 1 in the Jordan-Helder sequence of the product. Moreover, the socle is equal to the image of the intertwining operator that I discussed before. This, by the way, is a co-socle, so sometimes it's called also head and tail, so the intertwining operator takes the head into the tail, and also in the other direction. And consequently, that means that to check irreducibility, in principle, you just need to check that the intertwining operator, it doesn't matter which way, is an isomorphism, or that the socle is equal to the co-socle. This is, again, under this condition that one of them is square reducible, otherwise it's just not true. Okay, any questions about the statement?
Yes, so the second and the third and the fourth statements also need the assumption that pi is square reducible, or is this something general?
Or just the equivalence?
Just socle equal to co-socle of the opposite thing.
Oh, this.
Yes.
Yeah, no.
I thought that this is something
No, I think so, but
standard.
I don't want to say it under penalty of perjury, but I think so.
So in this theorem, so this pi and sigma, they're in principle representations of different JLNs, right?
Correct, yes. Yeah. Okay, now let's turn to the Zelevinsky classification.
You think so? You think that it's needed, yes? You think that the third and the fourth are not general, yes?
I think so, but
okay.
Probably somebody in the chat would be able to say it more quicker than me. Okay, so let's turn to the Zelevinsky classification. I'm sure that you're all familiar. I will just set some notation. So first of all, we'll just consider unipotent representation and only integral exponents. This doesn't matter. And a segment for us is something very simple, just a set of integers between A and B. And to each such segment delta, I attach a one-dimensional character of GL of the length of the segment, which is just determinant of the absolute value of the middle point. In other words, it's the socle of the principal series, absolute value to the A up to absolute value to the B. So that's called the Zelevinsky segment representation in this particular case. And there is a simple criterion for the irreducibility of a pair of segment representations, and it's called linkage, and that means that the two segments, the union, form a segment which contains both of them properly. And so this condition is symmetric, but you can break the symmetry, and this is just something very simple. So we said that delta precedes delta prime. If they are linked, either delta precedes delta prime or the other way around. And the simplest way to say it is this condition once you introduce this shift to the left and shift to the right terminology. So this is all very simple combinatorics. And now we can get to the statement of the Zelevinsky classification. So the main object are multi-segments. What are multi-segments? They are just formal sum of segments. Something looks superficially very easy. And we can always order in such a way that delta I does not precede delta j if I less than j, let's say by ordering the beginnings or the ends or the middle. And in this case, when you take the product, this doesn't depend on the order subject to this condition. So there is a well-defined module, which is called the standard module of the multi-segment. And the Zelevinsky statement is that the socle is irreducible of this standard module, and it occurs with multiplicity 1, in fact, in the standard module, and it gives you a bijection between multi-segments and the irreducible representations of GLN, in this case, under these restrictions. So that paper of Zelevinsky was the second paper, the follow-up paper with Bernstein, and of course, very much influenced.
So Zm itself is already irreducible?
Well, Zm is the socle, and the first claim is that it's irreducible.
Then it's socle of, okay, it's okay. And
socle is the sum of the irreducible representations, but in this case.
And Z of one segment I just missed, it is also the socle of the product, not the product itself?
It is a socle, but it's a one-dimensional character, in fact.
Z of sigma is a one-dimensional character. Delta. I see.
Of course, this is now the other way around. Right now, I order them differently. not like in the here. Here
Yes.
it will be the opposite.
They will be large.
Okay, so this is the statement. Any questions about this basic stuff?
One-dimensional character, you mean one-dimensional character times some Caspidal. So you also have some Caspidal representation, yes?
I'm
Or you don't
unipotent. I don't worry about
unipotent. So here is here unipotent? So
yeah, of
here,
course. The ear for me is just irrelevant here. But otherwise, it's just decoration. Otherwise, I just don't.
Yeah. Okay.
Okay. Now let's come to the whoops. Oh. Yeah. Sorry. So there is. If you don't like combinatorics, then multi-segments are a very simple object. They classify isomorphism classes of pairs consisting of a Z-graded finite dimensional vector space over C, let's say, and a degree 1 linear map. Okay, something very, very basic. I think maybe this geometry was the first or second page of Misha's talk yesterday, if I understood anything. And so the indecomposable objects they correspond to segments. You just take a Jordan block, graded Jordan block. So that's very simple linear algebra. And so the graded vector space will be the support, so to speak, of the multi-segment, the Caspidal support. And the Zerbinsky classification enjoys many wonderful properties. One of them is that if you take two multi-segments and you form the product of Zm and Zm prime, you are bound to have Zm plus m prime somewhere in the Jordan-Helder sequence. I'm not, cannot ascertain that it's in the socle or the cosocle, maybe it's somehow in the viscera, but it is there with multiplicity 1. So in particular, if Zm times Zm happen to be irreducible, then you know what it is. It will be the Z of m plus n prime. There's no, you know what is the label. And that will happen, of course, when the socle is Zm plus n prime, and also when you switch the rows. So I kind of break the symmetry here. So it's, you can think of it as kind of a condition and its symmetrization. And if one of them happens to be, at least one of them, happens to be square irreducible, then as I said, it's enough to check that Zm plus n prime is a sub. It embeds here. That will guarantee that it's a socle because the socle is irreducible by this KKKO thing. So far, so good. Okay, now let's go back to this non-square irreducible representation. The Leclerc example, I won't give all the details. Let me just highlight this guy. Okay, so it's a representation of GL8. You don't have to go beyond GL8. And I just ordered the end so that it's 5, 4, 3, 2. Okay, so it's descending. And the beginnings are 4, 2, 3, 1. 4, 2, 3, 1. What is 4, 2, 3, 1? Well, so I said that it was at the beginning, somehow people didn't have experience and they thought that every representation is irreducible, is square irreducible. And that somehow is reminiscent to Chevalier, who probably you know that he even put it in writing that he thought that every Schubert variety is smooth at all times before everybody was born. And that's of course not true. But in fact, even when he made this kind of idea, that was known to be true. He didn't know that, but somehow, so it's kind of amusing that these two things came about, which seem unrelated. But this 4, 2, 3, 1 is the first example of a non-smooth Schubert variety in GL4. And this is not a coincidence, as this result tells us. So now I consider a very simple, or just an example of multi-segment, where I take again the descending ends, and I take some permutation on the beginnings. Okay, this is some multi-segment. It won't appear so much in the unitary theory, but it's a legitimate representation. And then the claim is that the condition for square irreducibility, that's our result with Minguez, is that sigma is 4, 2, 3, 1 and 3, 4, 1, 2 avoided. What does it mean? It means that if you look at the metrics of the permutation, You cannot see a minor, which is a permutation matrix of 4, 2, 3, 1, or 3, 4, 1, 2. That's equivalent statement. So, you know, for this class of representations, square reducible are few and far between. And by the way, this condition can be checked in linear time, much to my surprise. Okay, this is just an anecdote. And that's the same condition as in the theory of Schubert varieties of smoothness of the corresponding Schubert variety. That was known, of course, much before. It's a result of Lakshmi Bai and Sandhya. In the 80s and the 90s, it was a very popular subject. Any questions about the statement? I will not prove, unfortunately, anything. But
so your proof is somehow, I mean, it's independent. So you're not relating this to Schubert's varieties. You're just computing it separately, right?
Correct. The proof is combinatorial and representation theoretic, and it's just by fluke. It's related. Very true.
But do you have an explanation for that?
No. That's your task.
So I just want to understand the parameter set. So Schubert varieties are parameters by permutation, yes?
Dima, you know what's the difference between good question and excellent question, right? A good question is a question that I can answer, and an excellent question that it's a question that I have a slide. So you have an excellent question. So let's consider the complete flag variety. And the Borel subgroup has finitely many orbits. That's Gauss elimination, which was known 2000 years before Gauss, and indexed by permutations. So these are the Schubert cells, the Borel orbits in the complete flag variety of GLR. And the closure is the Schubert cell, the Schubert variety, excuse me. Okay, Schubert cell is always smooth. It's just a fine, I mean, whatever. And the Schubert variety is the closure. And the orbit closure gives rise to the Chevalier order, which is usually called Buha order by accident. And okay, so every Schubert variety is a union of Schubert cells. And so the identity permutation, that's the close point. The longest permutation is the open cell, and the Schubert variety is everything. So it is smooth, but others are not. Okay, now for each multi-segment, I can attach, let's assume that now the multi-segment is regular. What does regular mean? It means that the AIs are distinct and the BIs are distinct. I do not exclude that the AI is equal to BJ. And I'm claiming that to each regular multi-segment, one can attach two permutations, sigma and sigma naught, such that sigma naught is less than or equal to sigma in the Buha order. How do I do it? Well, for sigma, it's something very simple. You just order the BIs that say that they are decreasing, and sigma will be it's just the relative order of the sigma, except with this, of the BIs and the AIs, except that with this convention. So sigma is clear. And sigma naught, okay, this is just a bit more involved. It's how the AIs and the BIs are somehow interlaced. And I won't go into this definition. This is the formal definition. Now, the sigma naught is not an arbitrary permutation. It depends only on the sets, not on the somehow fine on sigma, so to speak. It depends only on the set. And it's a special permutation. It's not an arbitrary permutation, unlike sigma. And I don't know how many people here read the famous book of Knuth, The Art of Computer Programming. Probably not many, because it wasn't in Bernstein's list of reading for the prospective students. But anyways, he proposes the notion of stack sortable permutation. This is just something very simple. And these are 2, 1, 3 avoiding permutations. So sigma naught exactly correspond to this. I mean, you can have many combinatorial ways to think about this. The bottom line is that for each multi-segment, regular multi-segment, you construct this sigma and sigma naught. If you're in kind of the situation that the sigma naught, the AIs are less than the BIs, then it's the identity. But somehow the opposite extreme is in the unramified case, and that's where sigma naught is equal to sigma. Okay, so this is just a combinatorial game. Yes, so I mean, the point was, maybe I should just go back a little bit and say that this theorem with limit, this as stands, it doesn't encapsulate the Leclerc example, right? Because here, you know, if it was like 8, 7, 6, 5, it would encapsulate, but this is more squeezed. So that's because of the sigma naught. Okay, So this is just combinatorial decoration, it doesn't matter. But here is the more precise statement, which I'm studying it because somehow of the geometry, not because of the decoration.
Does it encapsulate? You mean it's not regular?
It's not no, it is regular, right? It is regular, but it's not kind of wide. It's kind of squeezed. So let me. This will explain this. So now I start with any regular multi-segment. The Leclerc example is regular, but I have this sigma naught. And again, the claim is that the Zm is square reducible is equivalent to a geometric condition, but again, as Sasha rightly pointed out, it's only somehow a posteriori. So we don't, for us, this is just a black box. We don't say anything about that, but that's well understood, these conditions. So the smooth locus of the Schubert variety indexed by sigma contains the Schubert cell pertaining to sigma naught. That's a geometric condition, which can be explicated. I mean, it's equivalent to the Kazhdan-Lustig polynomial equal 1, but you don't have to compute the Kazhdan-Lustig polynomial for that. It's just this combinatorial condition, which is, you can check in like O of n cube or something. It's a very simple combinatorial condition. And there is also a representation theoretic counterpart of it, but again, this is not kind of our part. Our part is just one of the equivalents. All the rest was known before. And that is that when you express Zm in terms of standard modules, you can always do that, but the coefficients will be Kazhdan-Lustig polynomials. That's of course the relation to this. In this case, it just be plus minus 1. So it will be alternating sum. That means that the character is simple to compute. Because a priori, Zelevinsky gives you some procedure, some dictionary, some labeling of the representation, but he doesn't tell you, you want to compute the character, you cannot go to the supermarket with this result. But if it's such a simple sum of standard modules you understand, and you compute characters, decay modules, etc., at least at the level of semi-simplification. So this is the answer here. In some sense, it's most interesting in the case that sigma is the longest permutation, because here you really have the full thing, and this is called the terminantal formula. It was discovered by p-adic and some other people without knowing. Anyways, this is and also used by Arthur, by the way, in his book. Okay, so if we go back to this Leclerc original example, you see the 4, 2, 3, 1 staring at you, I hope. And then in this case, the sigma naught is not the identity, it's close to the identity, but the Kazhdan-Lustig polynomial is still not 41. Any questions so far?
Erez, I don't know if it's a central question, but so you mentioned that Kazhdan-Lustig polynomial being 1 is equivalent for smoothness. Is this clear?
Okay,
David Vaughan replied to me in chat that this is.
Okay, so of course, there are much wiser people in the audience than the speaker, but of course, that's a very special, that's a simply lace phenomena. That's not, it's rationally smooth, but here it's all the same. So,
thank you.
Okay, very good. So if there is a unanimous consent, I will proceed and to the geometry. So I like geometry very much, but unfortunately geometry doesn't like me back. Anyways, so there is more geometry in the, okay, let's just go back to, remember this graded vector space and this E plus V, the degree 1 linear maps. Now you can also do it for degree minus 1, right? It's the same price. And these spaces are in duality, and with the trace, with respect to the trace pairing. And of course, this duality is OT V invariant. OT V is the graded preserving automorphism, just the product of the GLA. And so, as I said before, it has finitely many orbits indexed by multi-segments. And the support is, the graded dimension of V, the isomorphism class of V. And whenever you have this situation, it's a very classical case. You can somehow, you have a bijection between the orbits. Orbits in V and the dual space. I mean, not V, but E of V. I mean, it's a linear action. How do you accomplish this bijection? So you consider the algebraic set, again, with an OT action of commuting pairs A from E plus and B from E minus. Okay, so it's some algebraic set. You have projection, of course, to the coordinates. The fibers are vector spaces. And this is this result of this old result of Piasecki, which gives you a bijection between the orbits of, let's say, E plus and the irreducible components of this variety. Okay, this variety will have irreducible components, and they exactly index the orbits downstairs, either in the plus part or the minus part. That's why you get a projection. Okay, so I'm sure that you're more than familiar with this kind of yoga. And what this gives rise to is, I said that these things are multi-segments also. And you have two bijections to the same thing. So that gives a bijection on multi-segments. This bijection is not identity. This bijection is non-trivial. And this is called the Levinsky involution, or some incarnation of the Levinsky involution. So, okay, this is just to set notation. So if you go from I will write the Cm, this is C, I guess, this letter. Cm will be the corresponding irreducible components in this commuting variety. And you can do it with the plus projection or the minus projection, and the difference will be this M sharp. This involution, so in fact it is an involution, and it was described combinatorially by Moglen and Walsperger. The representation theoretic context is that it interplays the Zelevinsky classification that I described with the Langlands classification, which is of course for any reductive group, but in this case it simplifies a little bit because the arguments are trivial, and where the building blocks are a twist of Steinberg instead of characters. Okay, so from now on I will just write, I will take the plus, just the convention. So Cm naught will be the inverse image of the orbit in the commuting variety, Cm will be the closure. So far, so good? Okay, so now we pass to this wonderful geometric condition, which in fact, I only learned about this after I worked with Alberto kind of started, and it was really very eye-opening to us. So let's look at the following condition, studied by Geist, Leclerc, and Schroer in one of the papers, again, in a very broad context, which I will say nothing about. And in this case, what it says is that, so you look at this connected component, reducible component rather, in the commuting variety, and you ask, now I said that on the E plus and the E minus, there are finitely many orbits, but of course in the roof, so to speak, in the commuting variety, nobody said that there are finitely many orbits. If this reducible component happens to have an open orbit, okay, so let's call this condition GLS in the name. The claim, the conjecture is that this is exactly characterized square reducibility. So this geometric condition characterizes representation theoretic condition. So they don't formulate it this way. Maybe they formulate some more conservative version, but in a wider context. But anyways, if it's wrong, then you can blame it on us, and if it's true, you can credit it for them. For sure, they are the first one who considered this condition, as far as I know. But again, there are many kind of variants and context. So is this conjecture clear? I mean, the statement?
So maybe you can recall the definition of XV, of
yes,
like Gothic XV.
So XV was the roof somehow making this bijection between the E plus orbits and the E minus orbits. It's very explicit. It's this commuting condition.
A, B.
So A is degree 1, B is degree -1, and they commute. That's the condition.
So E plus is this degree 1 important operator, where the orbits are exactly the segments.
Right. So both for E plus and E minus, the orbits are kind of in a superficial way indexed by multi-segments. But now the claim is that actually they have
the multi-segments. So the irreducible components of XV are naturally just a set of multi-segments. Yes.
Right. This, what I highlighted, is you can think of it as a set of multi-segments. Yes. I mean, with this, with this support, of course, determined by the graded dimension, by the isomorphism class of V.
Mm-hmm. So irreducible components of XV also in bijection with multi-segments, yes, because conormal bundles of orbits. Yes.
This statement says yes.
Okay. Yes. Okay.
Yeah, I mean, one has to digest this, and but you know, get used to it in some sense. Okay, so yeah, and I should say that you can check it very quickly, at least in a probabilistic way, if I'm going to be careful. Okay, so now we are in a situation that we have the theorem, remember, for regular multi-segments. It gave the geometric characterization, the smoothness condition. And then we have another conjecture coming from another source, but never mind, which also, in fact, it doesn't have this regularity condition, so that's very good. But it's kind of a different nature of conjecture, although it's also geometric, but it's kind of, first it's different geometry, and secondly, maybe it's different geometric, at least superficially different geometric condition. And now, and I should say, so okay, so of course once we saw this conjecture, the first thing was to verify that in the regular case it holds, and it holds. But it's not hard to check it. I mean, the same kind of proof also worked for this. But somehow we were very puzzled by this, because to have one nice condition is one thing, but to have two nice conditions, maybe that's too much to ask. But anyway, so we discussed it with Anton Melit, who is a colleague of Alberto in Vienna, and he came up with this wonderful conjecture, which I will run it on you, which somehow makes this bridge clear. So what does it say? It says that let's look at x less than w in Sn. So the Schubert cell of x is contained in the Schubert variety of w, and dually w naught is the longest element. The Schubert cell of w naught w is contained in x w naught x, which is the order, of course. And let's assume that x of w naught x is smooth, to be able to speak about the cotangent bundle. Anyways, so then the claim is that the following two conditions are equivalent. The first condition is what we had in our statement, that the smooth locus of xw contains yx. The second one is that the conormal bundle of this guy in the cotangent bundle of this guy has a dense B orbit. B is the Borel. And the conjecture is that these two conditions are equivalent. And you can kind of check this conjecture on a computer just to be sure that it's true. I don't have any intuition about this. But I should say that if X is stack sortable, so that was this 2-1-3 avoiding condition, which guarantees, so it's kind of a pattern of 3, which implies the two patterns of 4. So that follows from our theorem, but indirectly. So these two things have a representation theoretic interpretation in that case. And if you want to be on the sunrise side of the mountain, maybe in general, but I don't know.
So your proof is actually going through representation theory, or it's just combinatorial proof?
We have this representation theoretic condition, which we show that it's equivalent to this, and then we show that it's equivalent to the other. Of course, you can kind of untangle it to make everything is combinatorial anyway. So
combinatorial. So the proof of the fact that the geometric condition is conditioned for representation theory goes through combinatorics, yes?
Yes, and that's only.
So the proof of this conjecture is just you classify all cases, in both cases, combinatorially, and
okay. I mean, I say combinatorics. I mean, of course, representation theoretic, but there is a lot of combinatorics, coming from JK module techniques and stuff like that. By that, I mean.
So the proof is actual representation theoretical, yes?
Yes. No, it is representation theoretic, but kind of a combinatorial nature. That would be.
But the conjecture is purely geometric.
Right, the condition is purely geometric, but we just do it combinatorially. We just forget about all these things and just do it combinatorially. Okay, now I should say that this phenomena of a smooth geometric criterion and the open orbit geometric criterion, it appeared in other contexts I will say nothing about, but I will mention that. And one context is the context of Press and Anna Melnikov, and another context is Bernstein, Sakellaridis, and Venkatesh. And I will leave it at that. Okay, so now a few things, somehow some points of order. So first of all, I said that the GLS condition, that was the openness condition. I just want to make sure that we're on the same page in the book. So it can be checked very efficiently, because what does it mean? Remember, it's an open orbit on some variety, which is not it's not a vector space, but it's fibered over an orbit, right? So of course, to check that there is an open orbit, you just check that the stabilizer acts with an open orbit on the fiber, and now you have a linear action. So it's really a question of some vector space being a pre-homogeneous vector space, but the stabilizer is not reductive, so it's some linear group. But anyways, you can check it by passing to the Lie algebra, and you have a linear algebra condition. I will not go over it, but in principle, you just the question of there is some scalars so that it makes some vectors linearly independent. So that's something you can check on the computer if you at least on a probabilistic level. And the relevant sets, so everything is very down to earth. I mean, you have these relevant sets, which are pairs of indices when delta I precedes delta j, or the delta I shifted precedes delta j. It's kind of a fun thing to do. So where am I? Oh, okay. Okay, so now we come to the main, so I still have a few minutes, very good. So now we come to the main new thing, I hope. So now let's have two multi-segments M and M prime. And I told you that a multi-segment corresponds to an irreducible component in the commuting variety. So let's see M be the irreducible component in the commuting variety, and similarly for M prime. And now let's look at the sum. That also defines a component, in the commuting variety, which is of course pertaining to V plus V prime. That's what the superclassifier support is. And we have, of course, a diagonal embedding of xv times xv prime in xv plus v prime, under which the component of M times the component of M prime embeds in the component of M. And now there is a kind of a knee-jerk combinatorial, geometric condition, which is that maybe it's just that this is more or less the orbit of the, not the orbit, but you act by the automorphism of V plus V prime. So you can at least ask whether this geometric condition is sensible. Okay, so you started with this set, if you like. It's a subset of this component, and you act by the group, and you ask whether it's dense. And if you're lucky, then that will describe irreducibility. I don't know. You can always try. So that's actually not true. However, we have good reason to believe that if you add this one extra condition, that at least one of them is square reducible, a condition that you already saw that it's useful, then that we expect this to be the case, and I will give some evidence. So this is kind of the main slide. If so, you may want to spend a minute on that, and if you have any questions, that's a good time. So one remark that I should say, which is of course an obvious question to ask: what's the relation between this conjecture and the this GLS condition conjecture? So the answer is that they are not the same. So there is some distinction here. So in the case M prime is equal to M, this conjecture is not subsumed in the GLS conjecture. So of course, what we want, of course, is the same outcome. But because of this assumption, and if you like, I need to make this assumption exactly because these conditions are not the same, in fact. So this is a very strange situation. So these two conjectures they're not orthogonal, but somehow they have, of course, some common factor, but they are kind of not the same. So I don't know exactly what to make of it. I mean, in any case, these are conjectures, but I have some confidence in them. And so, but maybe you still ask that this, you can ask whether this geometric condition has a representation theoretic meaning. If not irreducibility, maybe something else. So the best that you can hope for, but it's not a conjecture because it's kind of a thin air evidence that we have for that the Zm plus M prime is a direct summand of the product. That somehow would be the most wishful thinking, the simplest you can think of, which is still consistent with what we have. But unfortunately, I don't know how to check this condition effectively. I mean, I would love to have a way to algorithmically check such a condition or just inclusion. embeddable. I just don't know. So anyways, don't take it too seriously, but of course it would be nice to have a conjecture which somehow subsumes these two conjectures together. So again, the conjecture 3 is assuming that one is co-reducible to get the reducibility of the product. The conjecture 1 is to say that Zm times Zm is irreducible, but it's not the same condition. So, I mean, of course, one is weaker than the other, but strictly weaker. Is it clear what I said, or am I just rambling? How to know in the Zoom you live in a different world. Okay.
Excuse me, can you hear me?
I cannot hear you.
Huh?
I cannot hear you.
Hear me?
Go on.
Yeah, can you show the slide for conjecture 3? I couldn't read the last line. It's not on there on my screen.
Oh, I see. I mean, if you click on the chat, then it will somehow make the last line disappear. I'm sorry.
I see.
Oh, yeah, I don't know. I mean, yeah, I mean, you can look at the slides. I mean, there is maybe somebody can put the link for the slides, then you could see.
No, what is the condition? Zm cross Zm prime?
The condition is that if you act on this set by the automorphism of V plus V prime, you will get a dense subset of Cn.
Okay, thank you.
Yeah, sorry.
Erez, you can exit full screen and then I think everything.
No, I am on full screen, but the problem is that sometimes the
yeah, I say you can exit full screen, and if you exit full screen, then the
somebody in the chat will probably help you. Okay, so yeah. Okay, now we have a refinement of this conjecture. Remember that the irreducibility condition, we broke the symmetry by making two conditions, one and the symmetrization. And in fact, you can make this also for this conjecture. You have to enlarge the set. So maybe that will also solve your problem. So this letter is called Y, by the way. So let Y be the subvariety of the component of M plus M prime, consisting of the pairs such that they preserve V prime. So remember, everything is on V plus V prime, right? So they preserve, the AB preserve V prime. They induce something in the kind of the open part of the connected of M prime. And when you induce it to V, the quotient, then you will get a pair in CM0. CM0, remember, that was just the inverse image of the orbit. And here it's important that I do the plus because I'm considering the Zm. I mean, the other condition is, the previous one was symmetric, somehow symmetric in this, but here I'm using the plus projection. And so this is a refinement of conjecture 3 because, again, once assumed this green condition, I said that the irreducibility is equivalent to this condition and the symmetrization. So if I know this, that, and of course also the right-hand side also be the same way, it's easy to check. So that's a refinement of this conjecture. And the interesting thing, but again, unfortunately, I don't have enough really hard evidence, is that as far as I'm concerned, this is also conjecture with Mingus, of course, it's in the same paper. And as far as I know, I mean, I don't have a counterexample for this, even without this green assumption. So unlike the previous one for irreducibility, well, it just flatly false without some kind of assumption, the way it's formulated, but, you know, maybe some smart people can amend it so it will be good. But I was not able to do it. Anyways, but this conjecture still, in principle, could still hold. But again, I don't have enough evidence because to go to the irreducibility, I mean, whoops. I mean, this sentence is true only under the green assumption. Okay, I hope it makes sense what I'm saying. And again, one can reformulate it in a kind of a linear algebra term. I won't say too much about this. You have, again, this very kind of simple combinatorial sets which kind of govern everything. And you see that the difference is that here you have kind of two sets of scalars. I mean, in the case M equals M prime, the GLS condition would be that the lambda ij is equal to the lambda prime ij. So it's a more stringent condition. It's strictly weaker. Okay, so what is the evidence for the conjecture? Well, so there is a nice class of representation which somehow reflects Verma modules of dominant weights. I will explain. And okay, we call it ladder representation. I was ignorant that this terminology is already kind of reserved, but anyways, I hope it's a different context. And that contains somehow Speer representation responsible for the unitary dual, and they are all square reducible. And our evidence is that if you have a product of ladder representations, then the conjectures hold, so both conjectures, the refined conjecture, for any n prime. So for certain class of representations, we know the conjecture hold for all n prime, and this class of representation contain generic, unramified, unitarizable representations, but much more, but again, not all square reducible, but some of them. So for a wide class of representations, we have the conjecture for any n prime. That's one of the main results in the paper. And a supplement condition is that you can actually say, so I said it's a product of ladder representation, but I want it to be irreducible, of course. I want that means that it's CM. And so that means that we better have some conditions to write conditions of irreducibility in this case, and that's also part of the game. But the bottom line is that there is a nice class of representations for which the conjecture is known for any m prime. And of course, I can switch the roles of m and n prime for conjecture 4. Okay, do I have any time actually, or do I need to stop? What's the situation? Dima?
Yes, you have 5 minutes.
Oh, I have 5 minutes. Okay, great. So let me end with some empirical results. So that's all what I can say about this business of square reducible. Now let's try to go beyond the square reducibility. And I already hinted that you can use some tools from other disciplines. And one of the fantastic things is what is called the Arakawa-Suzuki functor. They defined a family of functors from category O with respect to SLN or GLN to, well, not exactly Hecke algebras, but graded affine Hecke algebras that was good enough. And the bottom line is that you can express the standard module, let's say for multi-segment with R segments, in terms of irreducible representations, just like you do for Verma modules. Okay, so of course the Kazhdan-Lusztig conjecture, which is of course a known result. And so it's the same coefficient, the Kazhdan-Lusztig polynomials. And then you can, of course, you can turn the tables and express the irreducible guy by standard modules, by inverse Kazhdan-Lusztig polynomials, which are also Kazhdan-Lusztig polynomials. And now you can take a product for standard modules. You can easily make the product, and now you decompose back. So you do this operation on both, and then you do something, and then you do it back. And that involves Kazhdan-Lusztig polynomials for SR plus R prime, so the total number of segments, which can be expensive, of course. And if you want to do it empirically, so there is some limit. So just for the fun of it, I computed the Kazhdan-Lusztig polynomials of S12, all pairs in S12. It sounds a little bit maybe fishy when you first say it, because S12 has 500 million elements, and we're interested in all pairs. But okay, it's not all pairs. That's a non-starter. It's all you have some reduction that you can do, and then fortunately there are only 46 billion of these reduced pairs. And another somehow fluke, which is important, is that there are only 4.3. That of course we know only a posteriori, but we had the feeling that this should be only 4.3 billion distinct polynomials, actual polynomials, that you get this procedure. So some okay. So the bottom line is that you can put it in your computer or the Weizmann department computer, which has a 1 terabyte. Everything has to be in the RAM, of course. And this is all in this. These are the Kazhdan-Lusztig polynomials for S12. Okay, it's 500 gigabytes. And it took 1 month. Okay, so then I computed the composition of Zm times Zm for all m up to 6 segments. That's what I can do. And so I ran these results on David Kazhdan. I don't know if he's here. I hope he's here. And he suggested something which, of course, in retrospect is obvious, but I didn't think about this. To check the correlation between the length and let's say the dimension of the orbit space. So remember the GLS conjecture, or the GLS type conjecture, was that if there is an open orbit, so it means dimension 0, then the length is 1, it's irreducible, and that of course conforms with the experiments, otherwise I won't make it a conjecture. And if the dimension is 1, namely you have not open orbit, but codimension 1, then the length is 2. If the dimension is 2, you have lengths 6, 7, 8, 9, it turns out. The dimension 3 cases, these are the lengths that were produced. And there are also a couple of cases for codimension 4, which produced lengths 251, 257. Of course, it's just a question of how many, we cannot do it for more than 6 segments, otherwise you would have more lengths, I'm sure. So this table looks suspiciously like the number of infections per day of corona, which grows exponentially. But it's certainly a salient feature is that, there is kind of different regime. So the dimension controls somehow the regime of the length, at least. You don't have to have a degree in operations research to see some correlation here. And also I should point out that for length bigger than 2, it's never multiplicity free. This is the m times the m. The highest multiplicity is 9, and of course, you won't be surprised that it happens here. So this is just a table. You can do what you want with that. But it means that there is something here with this variety which somehow controls more things. It's not just having an open orbit, which is reducibility. There is something more, but it's, there are more questions than answers. The follow-up question was, can you somehow do it in a more refined way? So this is just the dimension, maybe some other invariants, but I didn't do anything about that because I need to know this geometric invariant theory better. And I should also point out that you cannot, I don't know, again, I think I said that I don't know how to make just algorithmically how to test this. That would be very helpful. So I don't know even if Zm plus m prime is always inside Zm times Zm prime. Maybe it's related to what I was asked before. So the last thing I will say, just 1 minute, I want to highlight this class of ladder representations, also tell some result of Max Gurevich, which actually led to more, but I won't have time to say on that. So in general, if you want to decompose pi1 times pi2, that's going to be a very difficult problem. That will not be kind of a polynomial time problem, that I'm sure. But there are cases, just like in the Levinsky case, you look at specific representation, there is some hope. So I think the good natural boundary are this ladder representation that I mentioned. Let me just give an example. So Max Gurevich showed that you're in a multiplicity free situation in this case, and you can describe it completely. He didn't describe the lattice, the module lattice structure, but maybe that's also on the table. But in any case, let me just give you a flavor of an example. So you took all these segments, 1, n, 2, n plus 1, 3, n plus 2, up to n to 2n. And then you split it alternating to the even and the odds, and you take the product. Okay, so you have this kind of picture. And you ask how it decomposes in the Grothendieck group. And it turns out that it has this answer. The answer, so a priori, you know that it has this form. The question is multiplicity free. So the question is which sigma arise, and it turns out that it's the 3-to-1 avoiding permutation. So it's a nice answer. The number of which is the Catalan number, which is, by the way, also the number of the 2-3-1 avoiding permutation. This is the book. Okay, so I think it's time to stop. I didn't say much about Joseph, but of course he's a great figure for us in Israel. He did so much to transform mathematics in Israel, and his influence cannot be overstated. And actually, behind this wall is his office. He's not there now, but Andre is sitting there at the moment. But I can attest that, he has a lot of patience to the students and to people, and it's really amazing to be around him. And he's really kind of our Zen master. And the last thing I will say that about his mathematics is that I somehow think of it as like an enzyme which decomposes complicated mathematical molecules to very digestible basic principles. That's somehow one of the imaginations I have about Bernstein, and I wish I had my enzymes, these Bernstein enzymes in my system. Okay, so many happy years and healthy years and fruitful years, and keep up this dedication that you have for mathematics, and just I wish you all the help in the world and the best in the world.
Thank you, Erez.
Erez, can I ask you a question? So, I mean, the bulk of your talk was about just the Wahori case, but you said that it's not really important. Is it really not? Is it obvious that it's not important?
In some level, yes. I mean, all the Hecke algebra is the same. Everything is kind of Hecke algebra theoretic. So I would say yes. If you want to make, if you want a reference, then okay, maybe you need to say some words. But this is not. In fact, Heilman has a paper where you can quote his paper for this equivalence. That would be the shortest answer. Because we are GLN after all, so there's only one Hecke algebra. All superclass values of GLN are born the same. That's the Bill of Rights of superclass value representations of GLN.
Erez, so in principle, there are other Zelivinsky conjectures that analog of Kazan-Lustig conjectures for this presentation of Hecke algebra, which in principle connect these multiplicities. And I think they are by now known, not that I remember the references, but so they connect these multiplicities and reducibility and multiplicities to geometry. Is this related at all?
Okay, so let me see if I can understand the question. So one thing is, I hinted about this here. So you can, the Zelivinsky conjecture that I think you're referring to, the old ones.
Yes.
They are how to decompose the standard module in terms of irreducibles.
Yes.
So they are certainly understood now, but I think what is good about this, you see, when Zelivinsky, when he originally formulated his conjecture, it was Kazan-Lustig of the GL where the representation is, and I should have emphasized this. That's a non-starter. The beauty of these Arakawa-Suzuki functors is that it gives you Kazan-Lustig polynomials for just the number of segments. So that's a different ballgame, of course. And now, of course, there is a relation between his Kazan-Lustig. After all, it's the same. It computes the same thing. And you can, in fact, there is some combinatorial apparatus. So Sarah Billy and Warrington have some worked it out, and maybe others. You can reduce from his conjecture to this thing. But this is a much more concise and better way to think about this. It also explains what's going on. I mean, it's a functor. It's a good functor, and you can literally go from category O of the number of segments of the GL of the number of segments to this GL. So that I think is the best explanation of that. Now about the irreducibility. So again, I could be missing many things here, but the irreducibility, the only way, kind of the naive way is what I said here, that you first express your irreducible guy in terms of standard module, and then take the product and then decompose. So it's kind of it's a non-direct way. So I don't know a direct way to say, it's irreducible if and only if some Kazan-Lustig polynomial is something. It's only a very complicated sum of Kazan-Lustig polynomial. In fact, it's called parabolic Kazan-Lustig polynomial. So in fact, we did interpret this. I don't have the slide. That doesn't make it a bad question, but if I had the slide, it would be a better question. Anyways, you can kind of translate it kind of mechanically to an identity of parabolic Kazan-Lustig polynomials. But I don't know what to make of it. It's just some fluke or something. I don't know if it answers your question.
Yeah. And another naive question. So in this Medel's conjecture, the statement in principle makes sense for any G, not just GLN, but is it known to be false in other types? I certainly would expect that it fails. But
which conjecture?
This Mallet's conjecture that you mentioned, that it was purely a geometric statement about smoothness versus orbits.
Yeah, I mean, the problem that I don't know, I mean, what is square reducible? It's just not,
no, but in Mallet's conjecture, there is no, it's Anton. Anton Melit.
Oh,
No?
Melit, sorry. Yeah, excuse me. Oh, Melit conjecture. Yeah, where is Melit's conjecture? The formulation certainly makes sense. I didn't do any experiments, so maybe Anton, is he here? Okay, anyways, the answer is...
I'm here, yes.
Okay, so maybe you can answer him.
What was the question?
If it's true for any Weil group, or any...
I mean, is it known to be false rather for other groups?
Yeah.
Oh, I didn't try.
Okay. Okay, thanks.
Further questions? And let's thank the speaker again. I would like to comment on Erez things that he said about Joseph. So I fully subscribe to both of them. So and I would like to add a little bit. We are both lucky, me and Erez, to have offices on two sides of Joseph's office at the Weizmann Institute. And I always want to talk to Joseph. I always need more and more of his advice. And I know ahead of time when he comes. So when I hear steps on the stairs, it means someone is coming to talk to him. And maybe in half an hour, he will come. So people are waiting, as several people gather, he comes. And then in several hours, this will be over and I will have a chance to talk. And about the enzyme, I also fully subscribe to this. And I should say that maybe Rami and me were even younger than Sasha and Dennis when we started to talk to him. And we got one more item on our list, what should we learn? And this is the only item that I managed to learn, and this is linear algebra. So you first learn linear algebra, and then all the things that I think Sasha or Roma listed. And I thought that with linear algebra, I'm fine. But this year, I had a problem, naively looking problem in linear algebra coming from more difficult representation theory that I could not solve. And Joseph showed that even a naive problem in linear algebra can be decomposed into two even more basic problems in linear algebra. And this advice helped me to solve this problem and derive some consequences. So thank you very much again for teaching us how to approach mathematical problems. And
when Joseph would give some kind of graduate course, the main prerequisite is that there was always good knowledge of linear algebra. And he always said that somehow you have to understand this problem. I mean, this good knowledge is a complicated notion.
Absolutely. This was the main prerequisite and remains one. All right, so we reconvene at 4:15 for the talk of Yiannis Sakellaridis.
Can you see my screen?
Yes.
Yeah, okay.
Yiannis, you did not send this to me, did you?
I sent it last night.
You sent it last night?
Yes. I mean, morning for you.
Sorry, I don't see it.
I didn't get it. So,
you didn't get it?
No. I don't have record whatsoever from any email.
So anyway, can you now share it through chat?
Oh, it's in my drafts. Apparently I didn't press send.
Okay, if you press send now, I can press it now.
I just sent it. Sorry.
Very good. So I will share it through chat.
You will put a link to the slides on the chat, or it's not a link?
It's not a link. It's possible to share a file. So I will now do this. Please tell me if it's if it works. Okay, so I'm sharing a file. Okay, did anyone receive it?
It's in.
Yeah, see, works fine, very good, thank you. All right, so I'm glad to present our next speaker, Yiannis Sakellaridis from Johns Hopkins University, speaking about periods and then functions.
Okay, thank you very much. It's really a pleasure to be speaking here. It's a great conference. Of course, by not being there, we're going to miss the most important part of the conference, which is when, after your talk, Joseph pulls you aside and says, I have a comment. And then he tells you something and it completely changes the way you think about what you just spoke about. So that we're going to miss, but hopefully at the next birthday conference, we're going to have the chance to receive those comments. I was a postdoc of Joseph's and for 2 years in Tel Aviv, and these were 2 years that completely changed my mathematical thinking. This is a photograph from the last seminar of the first year at Weizmann. We were having a seminar on the relative trace formula. Dima, I have a photograph right afterwards with you drinking beer. So you were probably there, but holding the camera. And Rami, I couldn't find him in the photographs. What's interesting is that what is on the board in this slide is also going to be my first mathematical slide. So I will start from there. I want to give an overview of work that has happened since then, because this work was greatly encouraged by Joseph Bernstein. Actually, the story starts earlier. It starts 2 years ago, 2 years earlier, 2004, in New York City. I was a graduate student, and I wrote, Peter Sarnak was at NYU back in the day. And I wrote to him, I said, I have money for a semester, can I come spend it at NYU? And he said, sure, if you don't need money, I'll give you an office. But he didn't only give me an office, he also invited his friends. And his friends were Joseph Bernstein, Andrei Reznikov, and Akshay Venkatesh. So you can imagine how decisive this semester was for whatever followed. Unfortunately, I don't have photos from this semester with Joseph or Andrei or Akshay.
Not even your residence in Harlem?
Well, I was not living in Harlem. This is from my window in Jersey City.
Okay.
I have many photos of New York. I just don't have photos with the people I'm talking about. And this is unfortunate because I could have had many embarrassing photos. For example, I could have had a photo of Akshay smoking a cigar. But unfortunately, I didn't take that photo. But it's true, though. Okay. So let me start from an example. Let's take X dots be a homogeneous space. It's going to be the quotient of n copies of SL2 by this unipotent subgroup. It's almost the entire maximal unipotent subgroup, except that you have this condition x1 plus x2 blah, 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 plus xn is equal to 0. This space has an action of SL2 to the n and of the multiplicative group, the diagonal torus, acts and preserves this condition. And this space gives rise to some some periods of automorphic forms that are known to be related to L functions. When n is equal to 1, this subgroup Hn is trivial, but if we also consider the action of the torus, like I said, you can relate this subgroup to the integral of a cusp form of a modular form over the diagonal torus. And this is the Hecke integral, which represents the L function of f at the standard L function of f. If n is equal to 2, this space can be embedded into a vector bundle over, well, I think I already, so I changed my group from SL2 to GL2 square, but doesn't matter. So it can be embedded into a two-dimensional vector space induced up to the group. And this is related to the Rankin-Selberg period. You can start with a Schwarz function on a two-dimensional vector space, and you can build an Eisenstein series out of that and integrate this Eisenstein series again against two cusp forms. So this is an integral on the diagonal copy of GL2 inside of your group of two cusp forms against an Eisenstein series, but the Eisenstein series comes from a Schwarz function on A2. And this is the Rankin-Selberg integral that represents the tensor product L function of these two cusp forms. And when n is equal to 3, it so happens that this space can be embedded into the quotient of SP6 by the commutator of the Ziegel parabolic. And in that case, you can form an Eisenstein series on a Ziegel Eisenstein series on SP6 and integrate it against, again, f of g. What is f of g? It is going to be a cusp form on the group, which is essentially 3 copies of SL2. So you form the integral of 3 cusp forms against the Ziegel Eisenstein series. And this is Garrett's construction, which represents the triple product L function.
Yiannis, I'm sorry, I don't understand something very basic.
Mm-hmm.
Just in terms of, so X is a certain set. What is its relation to the period?
Yeah,
I mean, what are you integrating over what?
I will explain. I'm not expecting the exact relation to be clear. I'm just making an observation that this space seems to be related to these 3 periods. So let me go a little bit historically. Back in the day, these 3 periods were considered completely different constructions. So the state of the art was summarized in a paper of Bump about the Rankin-Selberg method. And clearly n equals 1, n equals 2, and n equals 3 seem to be of a different nature. The first is just a period over some subgroup. The second is an integral against an Eisenstein series on a smaller group on GL2 embedded diagonally. And the third is an integral against an Eisenstein series on a bigger group. But what got me started in this subject is that I observed that these three cases had something in common. Namely, there was a space underlying those three cases, which was this homogeneous space, the quotient of the group by this strange subgroup. Okay, so I'm going to try, Dennis, to explain how to make this uniform and how to put those three cases in the same footing. My first idea was, well, since these three cases look very different, let's ignore the details and let's just integrate over this subgroup. So my first idea was, of course, the question is what happens when, how can you generalize this to higher n's? What should you do in order to get the n-fold tensor product L function? And the first idea was just consider the integral, the period integral over this subgroup. By the way, my notation is that brackets H, I wrote this in the previous slide, brackets G is the automorphic space, adelic modulo rational points. So this was the idea then. Unfortunately, I was in New York and I said this idea to Jacquet, and he said, no, this will not work. Because if you write down this integral, you're going to get an Euler product which has a natural boundary. It does not represent an L function. And then I also said this idea to Joseph, and he said, that's very interesting. I would be happy to discuss it further. And it turns out that Jacquet was right. And it turns out that Joseph was also right. So in order to explain what to do and how to unify these three integral representations, so let me fix ideas. By the way, all the formulas in these slides are approximate, and I'm omitting Archimedean places. You're not going to see the Archimedean factors. So you have a subgroup H. You take its automorphic quotient space. You can think of it as ban H if you want. So let me also take unramified level everywhere. So everything will be unramified everywhere. You embed it into the automorphic space of G. Okay, so I mod out everywhere by KG, which is the maximal compact subgroup. And for a cusp form on, or an automorphic form or a function on the automorphic space of G, I consider the period integral, but I want to write it in a slightly different way. It seems to be a singular distribution, an integral over brackets H, but since everything is already invariant under KG, you can also write it as the integral of your automorphic form against this smooth function, which is just the smoothening of the H period. So it's just the characteristic function of brackets H times KG. And we're going to call this the period distribution. So this is the period distribution. And here's a way to explain how it comes about. You start from something that knows nothing about automorphic space and arithmetic. You start from a Schwarz function on the homogeneous space G mod H, which is the characteristic function of the integers. So you start from the characteristic function of the integers on the space G mod H, and you form the theta series out of it, which is just the sum over all rational points on the homogeneous space of this function. So this way from the Schwarz space of a variety, you go to, you construct the smooth function on the automorphic space, just by this theta series, this summation over rational points of the homogeneous space. Is that clear up to this point?
So this theta series is a function on what?
So this is a function on brackets G. I should have written it. This is a function on brackets G. On bracket, it's a function on band G, on brackets G mod KG. Okay, so I start with an unramified function on G mod H.
Yes.
And I write down its theta series. So this is now left invariant under G of K. So it's a function on G adels mod G of K.
And you forget H. You forget the invariance with respect to H.
Here I have the notation. Can you see the notation slide? So I start with a Schwarz space of G mod H, which is here denoted by X. And I form the theta series, which is a smooth function on brackets G. Yes, I forget the space.
H. You forget H equivariance.
Yeah, I forget H equivariance.
Thank you.
Okay. But
yes, but X is not a group, so your notation is strange. So
sorry?
Your X is not a group, so it's not well. It's when you write it as a product. It's
X is the homogeneous space. So yes. X is G mod H in this case. X dot.
You mean product gamma times G doesn't really make sense.
There's no product
in the formula for theta series.
Oh, because G acts on the space. So gamma is in the space and G acts on the space by translation.
Okay.
Yeah. So, but as we saw by this comment of Jacquet before, the period distribution is wrong. So it's the wrong functional to consider. So the moral of the story is that considering this period distribution that comes from the characteristic function of the integers of G mod H may be wrong in general. It's not the distribution that will give you an L function. So how do we fix that? Well, back then I was studying the papers of Braverman and Kasdan, who defined a non-trivial Schwarz space for the basic affine space. The basic affine space is a generally singular space. It is the affine quotient, the minimal affine embedding of the homogeneous space G mod N. N is the maximal unipotent subgroup. This basic affine space generalizes the following, which is a smooth example. Take G to be GL2 and consider the, well, okay, or SL2 maybe, and consider the basic affine space for SL2, which is just, SL2 mod N is the affine plane without the origin, and then the affine closure of that is just the affine two space, affine plane. So what is the difference between Schwarz space of the open set and Schwarz space of the affine closure? Well, at any finite, not non-Archimedean place, the integers of of X dot are pairs X and Y, which are co-prime. So not both of them can be in the prime ideal. Whereas the integers of X are integral pairs X and Y. So the theta series in this case corresponds to the Eisenstein series, at least after you integrate against the character of the torus. So I integrate a Schwarz function over a character of the torus. I end up in a principal series representation. And then I apply this summation, and this is the Eisenstein series. And you can study the difference between starting with the Schwarz function on X dot and starting with a Schwarz function on X. Classically, the difference between those two is expressed in these two different Eisenstein series. One is the Eisenstein series where I sum over all pairs M and N, which are coprime. That corresponds to X dots. And the other is the Eisenstein series where I sum over all pairs M and N, let's say non-zero, but it doesn't really matter, actually. and this is another Eisenstein series. But in this case, whether you start from one or the other, the Eisenstein series does not have a natural boundary. It has meromorphic continuation, and the difference between the two Eisenstein series is just this zeta function at 2s. Okay. So this was the Schwarz space of A2 is the Schwarz space that was generalized by Braverman and Kasdan. And what lies behind their work is something that already had happened in the geometric setting, Drinfeld's compactification of band B. What is Drinfeld's compactification for band B? It is the space of maps from a curve, I should have said non-degenerate maps, from a curve to the affine closure of G mod n, divided by the action of the torus and the group. So this is the geometric incarnation of this local space. It's a global space over defined with the help of a curve, which we will think of this global space as modeling the local space that we were discussing before. So band B bar is singular, and we want to compute its intersection complex. So the basic idea here is that in this Schwarz space, let me just go back. In the case of SL2, X is a smooth variety, but in general, it will be singular. And the basic idea is that you want to consider the function on X of O corresponding to the intersection complex of the space. What does intersection complex mean? I will say it in the next slide. You want to think of X of O as being the points of some arc space, of the arc space of X. At least in equal characteristic, you can do that. So you want some function that comes from geometry and mirrors the singularities of your space. So this is what is going on in this slide. You have, so function theoretically, what you want is, you want a function on, you want to have a Schwarz space on your variety, which the variety itself is singular, and you want to define some kind of Schwarz space on your variety, which includes a distinguished function, and this distinguished function will be the one corresponding under a shift function dictionary to intersection complex. I will use IC to denote this function, not just the complex, by abuse of notation. And here, O is, this bracket should be angular. O is the ring of Taylor series over a finite field. So, and we think of X of O as the F points of the arc space of X, which will be denoted by L plus X, so maps from the formal disk to X. Again, I'm shifting between general local field and equal characteristic, but morally the story is that we want to consider the IC function. In the case, and this space band B bar is just a global model for this local arc space. And more precisely, the IC function of band B bar should be thought of as the theta series that I wrote before, applied to the IC function of the local Schwarz space. So we have a local Schwarz space, which contains a distinguished element, which is this IC function. And we do this over all places. So we get an adelic function and we apply the theta series to it. And the output of that is the IC function of band B bar. And a result of Braverman, Finkelberg, Gates-Corey, and Mirkovich computed this IC function. So this is, like I said in a previous slide, this theta series in this case is just an Eisenstein series after you integrate against the character of the torus. So if you integrate against the character of the torus, you get an Eisenstein series. It's the analog of E star. And BFGM computed what this Eisenstein series is and how it's related to the standard Eisenstein series, not only for the principal case, but for all parabolics. And they found that the quotient of the two is again this product of L functions. These are always Langlands-Shahidi L functions, of course. Okay, so we have these two different Eisenstein series, one from the homogeneous space G mod n and the other from its affine closure.
Is that product a finite product?
Yeah, so this is a product over all positive coroots. So I compose the character that defines the Eisenstein series with a coroot. So it's a finite product of abelian L functions in this case. In the general case, it will not be abelian L functions, it will be Langlands-Shahidi L functions.
And can you recall what is the IC function of a space?
So it is the function that you get by applying trace of Frobenius to the intersection complex. So this will be a function on, well, okay, I'm abusing, yeah, I guess I'm computing here the push forward to band G. So this is a function on band G. This is a function on the automorphic space of G in this case. Okay.
Okay.
All right. So let's go back to a more general space. We want to produce various L functions, and the idea of working with the standard test functions on G mod H did not work in general because these correspond to the period. So what is the idea? The idea is to choose some affine embedding of our homogeneous space G mod H. For example, you can take the minimal affine embedding again. Define a Schwarz space which will contain a basic vector, and the basic vector will mirror the singularities of your space. So it will be the IC function of the integers of X, of the arc space of X. And then you want to define the X period as the theta series, which is obtained by summing over all rational points. So all of these things need to be defined. They don't, these notions, none of these notions made sense back then, but still I wrote a paper and I formulated a conjecture that the referee who is here, I'm sure in the audience, he wrote that it was a lot of wishful thinking. So the conjecture says that if I start with an automorphic form, suitably normalized, for example, you can normalize it by the Whittaker coefficient, and you integrate against the period, the X period, which is this theta series obtained from the IC function, then this will be equal to a special value of an L function.
Yeah, okay. So is it supposed to depend on the embedding on X or just on an X dot?
So it's supposed to depend on the embedding.
Mm-hmm. Thank you.
Yeah. So X dot itself does not give you the correct answer. So then you take an IC function coming from an embedding, and the answer is going to depend. But when I say the answer, I mean the L function that you get. And actually, I will show examples here. So the basic example answering your question, Dennis, is when you take X dot to be a group, GLN. So this is already affine, but I choose another affine embedding of this, which is the space of n by n matrices. So here the group acting is two copies of GLN on the left and right. But I have to take my automorphic form to be of the form phi tensor phi dual, phi bar. And then the period integral that I wrote before corresponds to the Godoma-Jacquet integral. There is a mistake here in
in the equation on the left, I have unfolded the integral. So here on the left, it should be just adelic points, not automorphic space, because I unfolded the summation. If you unfold the summation that defines the theta series, you end up with a Godin-Jacquet integral, which is the integral of matrix coefficients against Schwarz functions. And this gives you special value of an L function. Okay, so here you see that the L function depends on choosing a different embedding from the standard one. And this construction of Godin-Jacquet you can generalize. So there is this L monoids that were defined by Ngo, but they were already existed in the work of Braverman and Kardan. If you take any group, any reductive group, let's say split, which has some kind of determinant map, and you take a section of the determinant map, this section is a co-character for the group, so it defines a character, a weight for the dual group. So it corresponds to a highest weight representation. And in work with Boutier and Go, we proved that in this case, first of all, we proved that the IC function makes sense, even though one thing that I didn't mention before is that the arc space is infinite dimensional. So a priori, it's not clear how to do perverse sheaves, how to define perverse sheaves on this space. There has been work consequently by Boutier and Kasdan and Warshawski on this. But back then, we didn't have a definition of perverse sheaves. And we showed that nevertheless, because the singularities are finite dimensional by the Greenberg-Kasdan-Drinfeld theorem, you can make sense of the IC function. And then we computed this IC function in those cases, in the case of L monoids. And the lambda, the co-character lambda of the group that defines this monoid is going to also determine which L function you are going to get as an output in this case. So this is a generalization of Godin-Jacquet. Of course, let me clarify that all of these are local facts. If you consider the global integrals, they will converge somewhere. And the elephant in the room, and I don't have much to say about the elephant, is how do you prove analytic continuation and functional equation? However, it's important that these L functions come out in a natural way from some natural function or distribution that is given by geometry.
But in terms of your conjecture, you believe in it even when X doesn't have multiplicity 1, say?
Yeah, no, did I mention, I did not mention it before. So no, the conjecture is for spherical subgroups, satisfying also some conditions for spherical spaces. Yeah. So the general case now, what is the L value attached to a general spherical space X? First of all, so in other words, I'm asking if I give you some spherical, not homogeneous, some spherical space, spherical affine space, and I make this construction, the period is expected to spit out an L function. What is this L function? Which L function will it spit out? For example, the VL that you see on the last line here. This is an irreducible representation of the dual group. So which irreducible representation is it? So first of all, let me clarify that here we're not talking about the whole dual group, but about a subgroup of the dual group, which is the Gates-Corin-Adler dual group, because not every representation will have a non-zero period. You cannot integrate any kind of automorphic representation against your period distribution, only those automorphic representations which come from a certain subgroup of the dual group, whose Langlands parameters come from a certain subgroup. For example, when X is the group and G is H cross H, then we're considering the diagonal period. In order for the diagonal period not to vanish, you cannot put arbitrary representations on the two copies of H. You have to put dual representations on the two copies of H. So your representation has to be of the form pi tensor pi dual. So the dual group of X, of the space X, is just the dual group of H. It's not the dual group of H cross H. So we're looking for a representation of the dual group of the spherical variety. So already when I was a postdoc of Joseph's, again, motivated by, definitely encouraged by him, I was computing such a formula for the case where X is already homogeneous. So X is G mod H with H reductive. So the IC function is very simple. It's just the characteristic function of the integers. And then there's a general formula for the L function that is associated to that. And the formula is expressed in a combinatorial way in terms of the so-called colors of X. Let me say a couple of words about what are these colors, because they're important. They determine this representation of the dual group. So if I have a spherical variety, it contains an open Borel orbit. So if I consider the quotient of the spherical variety, the invariant theoretic quotient, by a maximal unipotent subgroup, it becomes a almost homogeneous space for the universal Cartan, for the torus of G. And in fact, the torus of G will act through some quotient, and this quotient I denote by T sub X. So I have a toric variety for T sub X, and it's an affine toric variety because I started with an affine space. And so by definition, a toric variety is given by a certain cone generated by all those co-characters that have a limit in the toric variety. So the generators of this cone correspond to co-dimension 1 Borel orbits on the original space, and these are called the colors. And to each color, you attach a co-weight of the dual group. It's precisely the co-weight that converges to the corresponding divisor on the quotient X mod n. So the geometry of the spherical variety gives rise to certain co-weights of the torus T sub X, and this become weights for the dual torus, which is the maximal torus of the Gates-Corinne-Adler group. So, and these will be the weights that appear in the representation rho X that we're looking for. So we're looking for a representation of the dual group, and we can see which representation it is by computing these colors, by computing the co-dimension 1 Borel orbits, by computing the valuations induced by them, or in other words, by computing the data of the quotient variety X mod n. So for example, in the group case, so my space is H, and the group acting on it is H cross H. So the colors in that case are the Bruhat divisors. They are the co-dimension 1 Bruhat cells. And each one of them induces a valuation equal to a simple co-root. And these simple co-roots are weights of the adjoint representation of the dual group. So in that case, the representation of the dual group attached to it is the adjoint representation, or the co-adjoint representation if you want. You will see later that the co-adjoint representation appears more naturally. What is the meaning of this calculation in terms of L functions? The meaning is that if you consider the Peterson inner product of two cusp forms normalized by their Whittaker coefficient, then you obtain the adjoint L function at the point 1. So the Bruhat divisors, which correspond to coroots, give rise to the adjoint representation of the dual group. Again, this is a combinatorial recipe for now, but that's what it is.
Yiannis, this combinatorial recipe, is it precise, or is it also approximate, or is it precise?
It's precise. It's precise, but it doesn't a priori see why the result is a GX check representation and not a virtual GX check representation. So the combinatorial recipe actually gives you some virtual character and a priori.
Multiplicities of weights in this way.
Sorry?
Can you see multiplicities of weights in this way?
You're not going to see all the weights anyway. So you see, for example, here you see only the simple coroots, and out of them you have to say that you obtain the whole coadjoint representation. So this is just a recipe that tells you how to, how should I say? Yeah, so it's just a combinatorial recipe that produces an L function, and a priori it's not clear why it is an L function. So even the multiplicity is not, it's not a priori clear, but it so happens that it does. In any case, the L functions that you see out of these examples do not have, they're very limited. So you cannot have multiplicities, or at least high multiplicities, in these L functions.
Well, for the adjoint representation, the zero weight has a big multiplicity. So
yeah, but the zero weights you add in afterwards. You will not see it out of this combinatoric. So the zero weight, for example, doesn't appear anywhere in my description. So another example is the triple product. Consider the quotient of PGL2 cube by the diagonal. So then Borel orbits here are equal to, are the same as PGL2 orbits on 3 copies of P1. So you have an open orbit where the 3 points are distinct, and then you have codimension 1 orbits, the colors, where 2 of the points on P1 coincide. And for each such orbit, if you compute the data of the toric variety, if you compute the valuation, you see a co-weight of the form alpha I plus alpha J minus alpha K. And again, these are weights for the triple tensor product of standard representations of the dual group. And because these weights appear, this corresponds to the Watson, Ichino, Kudla, Harris, Gross, Bocherer, Schulze-Pilot formula for the triple product period. The fact that if you take the square of the integral over the diagonal of PGL2 of 3 cusp forms, then this gives you the L function at the triple product L function of the 3 representations.
Sorry, and from this kind of analysis, is it possible to see that, is it possible to explain why in the first example you just have the period and in the second you have the square of the period?
Yeah, so this is because I didn't get into details about how to normalize things. In fact, the 2 examples are completely uniform if you normalize things correctly. Morally, you should normalize by the Whittaker model, but because not everything is generic, that what you should really do is take the square of the period, divide by the inner product, and normalize by the formula expressing the Peterson inner product as an adjoint L function. So these are all details that I have swept under the rug, but believe me that these 2 formulas are the same in the end. So really they are about the square of the period of automorphic forms suitably normalized. Okay.
Okay.
Yeah. So, okay, so this paper, the older paper of mine that I mentioned, was only for Gmod H with H reductive. So the question is, what happens in more general cases? Can we say something about the conjecture that says that if I take a general affine spherical variety and I consider its intersection complex and take a function out of the, make a function out of this and produce an automorphic distribution, then this will give me some L function. Can we prove that, and can we calculate what this L function is? And in ongoing work with Jonathan Wang, that I think is almost complete. So the results that I will mention here are not complete, but I think we're confident that we have all the ingredients that we need. And this is really, I have to say, mostly work of Jonathan Wang. We have generalized the formula that I said before and the setup of Boutier and Go, although for now we have this restriction on the dual group. So literally speaking, it's not a generalization of the work with Boutier and Go, but all the ingredients are there. So it's a description of the IC function for every spherical variety, affine spherical variety, in a similar way as the description that I gave before for the homogeneous case. And for example, if we go back to the original example of my lecture, which was a family of spaces for the group SL2 to the nth power, and you take the affine closure of those spaces, then integrate a cusp form against the period distribution coming out of the IC function. This integral converges when the corresponding character is large enough, and it gives you the tensor product L function evaluated at a half. Okay, but this one half, sorry, this one half is wrong. It should be, sorry, this is very important here. This should be 1/2 plus S. Okay, so my group acting, I have a multiplicative component to my group, and for now, this only converges for real part of S, very large.
So just to make sure that I understand that, except for the convergence, this is a local statement, right?
This is a local statement. This is a local. This is a local statement. So there is this question of how you go from the global statement to the local statement, and that's what the next slide is about, the Euler factorization.
Just 1 second. So
yes.
Just to make sure. So 2 questions. Is it again that you're getting the square of the value of the L function, or just the L function itself?
You get the L function itself, but if you want to connect it to what I was saying before, you should take, so the pertinent representation of the dual group here is not the tensor product representation of the standard, but it's the tensor product of the standard plus itself, or plus its dual.
I see. So in
for the square, you would just square your L function. So the pertinent representation of the dual group here that corresponds to the square is the tensor product of the standard plus the dual of the tensor product of the standard.
I see. So in particular, in the work with Jonathan, you exhibit the representation, right?
We do not exhibit the representation. Again, we give this combinatorial recipe. Basically, what we do is we compute the IC function and its nearby cycles for the universal degeneration. The nearby cycles are related to the next slide that I will say. So we compute the nearby cycles, but this is function theoretically. This gives you a function on the torus. It doesn't give you. It gives you a representation of the torus. It doesn't give you a representation of the group. And
I have a question.
We notice that we get a representation of the group. Yes.
There should be an S in the formula, as you said.
Yeah, I corrected it.
And that's true for real S large. Do you know this actually is continuable in S?
Yeah, no. Like I said, I have nothing to say about the elephant.
Okay.
Yes.
Thank you.
So there is a question of how do you go from the global period to the local calculation, and this is in some cases a very easy step. For example, in Godemaja-Jacquet, Hecke, Rankin-Selberg, there is some kind of unfolding process that immediately turns your global integral into an Euler product, and in some cases it is a very hard calculation, a very hard result and conjecture. For example, in the Gann-Gross-Prasad cases that you see on the slide, it is still unknown that the period or the square of the period is equal to an Euler product. So this is the content of the Ichino-Ikeda conjecture. If X is the quotient of SON times SON plus 1 by the diagonal of SON, then we would like to write the square of the period as an Euler product, and Ichino and Ikeda produced an explicit formula which is Eulerian, conjectural. Then actually Venkatesh noticed, and that was the beginning of our joint work, that the right-hand side has a meaning in terms of the Plancherel formula. So remember that in this case, the period is obtained starting from the characteristic function of the integers of our homogeneous space, because this space is smooth. And you can express the output of the right-hand side, the local Euler factors, in terms of the Plancherel density of this function. In other words, when you write down the Plancherel formula for this function on the space L2 of X, so this is again a completely local statement. When you write down the Plancherel formula, you are going to get an integral over all unramified representations of certain functions integrate against the standard Plancherel measure. And of course, there's no a priori reason why these functions should be L functions. There could be arbitrary functions of your unramified representation, but they turn out to be L functions. So there are two statements here. The first statement is that the global period is equal to a local period, a product, an Euler product of local periods which are related to the Plancherel formula. And the second statement is that miraculously, when you write down this Plancherel formula, you see L functions. So using this observation, we generalize the Ichino-Ikeda conjecture. So now, based on this generalization, if you want to compute what is the, if you want to say what the global period will be equal to, or the square of the global period, the Ichino-Ikeda conjecture generalized will give you an Euler product of local Plancherel densities. And then a local calculation will tell you that the Plancherel densities are actually equal to L functions. And what we actually did in these previous works that I mentioned was this entirely local calculation of Plancherel densities for our basic function, which is the IC function.
Sorry, can I just repeat my question from before? So why, I mean, how do you know that sometimes you have to put the square and sometimes you don't have to put the square? It seems like magic to me somehow.
No. I always have to put the square. In the examples that you didn't see a square, it so happens that, if my L function is of the form a representation times its dual, right? If the representation of the dual group can be written as the cotangent space of a representation, then you can break up the corresponding L function into a product of two factors. And you can expect that each of them will correspond to the period without the square.
So you can only know such a thing from the answer. So if you just look at the period itself, you wouldn't know when the period itself and not its square would have something to do with the function.
That's right. You see what the answer is, and in some, of course, I mean, that's not how it really goes in real life. In real life, there are cases where you can actually just write down the period and do a manipulation of it by some kind of unfolding or some other manipulation and directly show that it's an Euler product, and then you compute the local factors. And that's how it works in real life. But in terms of this general conjecture that I presented, you can calculate the answer, and then sometimes the answer is not an irreducible representation of the dual group, but it's a representation plus its dual. So, and in that case, you can expect that you have a formula for the period itself.
Can I say something there?
Sure.
The fact, if you self-dual and you go to the central value as he's going, the fact that this is non-negative is a highly non-trivial thing. It follows from the Riemann hypothesis of the L function. And there's a beautiful paper of Rallis and Lapid, which explains that for half of these L functions in the world, one can prove that. For the other half, we desperately want to know that consequence. So this is a subtle point. Even the non-negativity is a very deep point.
Yes.
In the number field case, anyway.
Yes. Yeah, so in some cases, it so happens that the square is an L function. In other cases, it so happens that the square is an L function, but this L function can be written as a square, so absolute value square. So that's all that's happening here. Okay, so this finishes what we already know, modulo of course, the very big Ichino-Ikeda conjecture and its generalizations. Now, we're looking for a reason why this is happening. We're looking for a reason why the Plancherel formula gives rise to actual L functions. And so I come to the last part of my talk, which is a geometrization of the Plancherel formula. So why do L functions appear in the Plancherel decomposition? So this is now based on ongoing joint work with David Benjvi and Akshay Venkatesh. So the Plancherel decomposition of this function can also be expressed in a more algebraic way, in a more shift theoretic way. So let's put ourselves into the setting of a local field inequal characteristic. Then we can think of our functions as Frobenius traces of L-adic sheaves on the space X of f, which we think about geometrically. So X of f will now be the loop space of X, and our sheaves will be invariant under G of O, which is the arc group of G. And then there is a formula for the inner product. So the inner product that appears in the Plancherel formula can be written as a Frobenius trace on the homomorphisms between two sheaves, the sheaf corresponding to one function and the Verdier dual of the sheaf corresponding to the other function. Everything here is in the derived category. So when I say homomorphisms, I mean X. So we are led to study the derived category of L plus G equivariant sheaves on the loop space of X. There may be technical difficulties in defining this in the singular case, but let me skip that. And one example is the group case where X is H and G is H cross H. And then in that case, the category that you see here is the bounded derived category of L of H, L plus of H equivariant constructible sheaves on the affine Grassmannian of H. And in this setting, we have the result of Bezrukavnikov and Finkelberg, which is the derived Satake equivalence, the Satake equivalence not just for perverse sheaves, but for the entire derived category, which says that there is a natural equivalence of triangulated categories between constructible sheaves on this quotient, H of F mod H of O mod H of O, and coherent sheaves, or everything is a DG category, so perfect complexes of coherent sheaves on the quotient of the dual Lie algebra of the dual group H hat star by H hat. So these are H hat equivariant coherent sheaves on H hat dual, or another way to think about it, it's the quotient of the cotangent space of the dual group by the action of two copies of the dual group by left and right multiplication. Now, we looked at this result and we realized that this cotangent space, or this coadjoint space that appears here, matches the adjoint or coadjoint L function that appears in the Peterson inner product of two cusp forms. So when we compute, as I mentioned before, when we compute the diagonal period of cusp forms normalized by their Fourier coefficient, then this is known for GLN, and it's a conjecture in general that this is related to the adjoint L function at 1. So we're generalizing this to a conjecture about arbitrary spherical varieties. Given a spherical variety, there should be some symplectic, some Hamiltonian space for the dual group, together with an equivalence of module categories for the spherical category. So on one hand, we have what would be the shift theoretic analog of unramified functions on X of F. And on the other hand, we have coherent sheaves on G-check equivariant coherent sheaves on the dual Hamiltonian space. And what does this Hamiltonian space have to do with the L function that I was talking about before? This Hamiltonian space is actually induced from this representation of the Gates-Corinne-Adler dual group. So the conjecture is that the dual Hamiltonian space attached to a spherical variety is the space of this representation of the dual group that I was talking about before, induced up to G-check.
So this is not necessarily.
I cannot hear, the voice has been cut. Hello? Okay, so I will continue, but if the voice...
Yes, could you repeat your question because you disappeared?
Okay, so I will continue, but if Sasha fixes the problem, then...
So let me ask instead of Sasha, what is Hamiltonian dual? Is it something we're supposed to know?
Sorry?
What is Hamiltonian dual?
I just said that there is a Hamiltonian G-check space.
So the notion of Hamiltonian duality is something known, or it's...
No, not as I don't have a definition for this.
I see. Okay.
I don't have a definition for this, but maybe this gives an. Maybe this gives. Yeah, I don't have a definition for this.
Thank you.
Just these examples. And another observation is that the association that takes you from the cotangent space of your original variety to its Hamiltonian dual is an involution. So in other words, if the Hamiltonian dual also happens to be a cotangent space of some spherical variety, then its dual is M. You were referring to, yeah, Dennis, Hamiltonian dual here is defined in terms of this conjecture. There's no other notion that I know of.
That was the question. Thank you so much.
Okay, so let's see some examples. So just to be clear, this conjecture will answer the question of why you have an L function appearing in the local Plancher L formula. Because if you go back to the previous page, then in terms of this conjecture, you can compute the homomorphisms between two sheaves and the trace of Frobenius on them, and you can see that from the description on the right-hand side, in terms of coherent sheaves on the Hamiltonian dual, you will see an L function popping up, the L function that I talked about before. So this will prove, this will in particular imply the conjecture on the formula on the Plancherel formula. So here are some examples. If the space is, if the space X is a group, so M is the cotangent space of the group. This is the case of Bezrukavnikov and Finkelberg. The dual is the cotangent space of the dual group. And like I said, this corresponds to the calculation that the Peterson inner product of two automorphic forms is equal to the value of the adjoint L function. Second example is you consider the Whittaker cotangent space, the Whittaker period. In this case, we say that the L function is equal to 1 because everything is secretly normalized by the Whittaker period. So the dual space is trivial. There's no L function. There's no representation. The dual space is just a point. But then here you can see the duality. The point is the cotangent space of a point. So it corresponds to the period here. It should be G check. It corresponds to the measure, to the volume of the group. And if you compute the volume with counting measure with respect to the maximal compact subgroup, then you see an answer which is essentially an L function attached to the space T star mod W with an appropriate Galois structure. So this is the motive of G, and this computes the volume of the group. This is not the Tamagawa volume. It's the it's a volume with counting measure, and you see now the duality. This space T star mod W is the constant section, and the cotangent space of the Whittaker model is induced from the constant section to the group. The next example is Tate's thesis. Your space is A1, so its cotangent space is T star A1. So the dual space is again T star A1. Why? Because the corresponding global period gives rise to the L function attached to the standard representation of the dual group, of the multiplicative group. So again, you get Tate's thesis here. If you consider periods of PGL2 automorphic forms over the torus, that's the first example that I mentioned today, you get the standard L function of the dual group. This corresponds to the dual Hamiltonian space being the cotangent space of the standard representation under the action of SL2. On the other hand, if you compute periods on this side, these periods on this side basically correspond to the calculation of Eisenstein series that I mentioned before. So what you get is you get this L function, this abelian L function coming out in the calculation of Eisenstein series. And this abelian L function corresponds to, so you see this weight alpha check here, and this corresponds to a representation of the torus that if you induce up, you will get the cotangent space of PGL2 mod GM. Oops. And the last example is the Gross-Prasad period. We mentioned that the square of the Gross-Prasad period is expected by the Chino-Ikeda formula to be equal to an Euler product. This Euler product evaluates to the tensor product L function at a half. So the dual Hamiltonian space is the tensor product of the standard representations of SO2n and SP2n. This is the standard symplectic space with an action of this dual pair. And vice versa, if you consider the period associated to this. So here, this is not a cotangent space, but it has a quantization, and you can think of the period as a quantization of some symplectic Hamiltonian space. The quantization here is the Veil representation. So if you write down the corresponding period in terms of the Veil representation, you get the Rayleigh's inner product formula. And the Rayleigh's inner product formula is expressed in terms of the standard representation of SO2n in that case. So the L function that you're going to get will allow you to reconstruct this original Hamiltonian space. Sorry, I'm not going into too many details here, but just want to say that you can compute periods on either side, and the other side will give you an L function. And just to remark, all these examples are spherical and multiplicity free. And they're also smooth. You can also produce examples where one side is not smooth, and then the other side will not be spherical. For example, you can produce examples that came up in the talk of Sasha Braverman, where you have, on one side, you have toric stacks, not toric varieties, but toric stacks. And on the other side, you're going to have representations of a torus, but without a dense orbit. Or you can produce some non-multiplicity free examples that I think Akshay Venkatesh will talk about in the next lecture. So let me not say anything more about this. Hopefully this dictionary will give rise to some new conjectures about things that we don't know. So many open problems. First of all, proving the geometric conjecture. There are some recent new cases by Braverman, Finkelberg, Ginsburg, and Travkin. We also have a ramified conjecture, and in the case of Tate's thesis, it has been proven by Raskin. And of course, the question is whether this calculation of the Plancherel formula can be upgraded to a conjectural categorical equivalence. Second example is, the second big question is to prove the Euler factorization, prove the generalization of the Ikeda formula. Only thing I want to say here is that I have suggested that this could be done by a non-standard comparison of trace formulas, and the geometric setup that I talked about suggests the existence of such a comparison corresponding to a map between Hamiltonian duals from the Hamiltonian dual of a space X to the Hamiltonian dual of the Whittaker space, which is just trivial. So the geometric setup suggests a comparison. And the last thing to say is the functional equation. I don't know how to prove it, but there should be some Fourier transform and some Poisson summation formula somewhere. Of course, that's the biggest of these problems. Again, the geometric setup suggests the existence of such a Fourier transform. So I'll finish here, and sorry for going over time. Joseph, thank you for all your encouragement and all your ideas. And I hope we'll be back many times to celebrate your birthdays.
Thank you.
Maybe a couple of brief questions, please.
This conjecture with David Ben-Zvi and others, it seemed to involve similar ingredients to real geometric Langlands conjectures proposed by Ben-Zvi and Adler like 10 years ago. Is there?
I don't know.
Okay.
I don't know. I'm not familiar.
Okay. Any other questions? Okay, then.
Ask about the meromorphic continuation in not the number field setting, but in the geometric setting. Are there any tools that might allow that in this, for example, for your case of n tensor products of GL2?
Well, in the geometric setting, you have an interpretation of the L function in terms of cohomology over the curve. Then you have Poincaré duality. So,
but can you make use of this kind of harmonic analysis to see it
No, and actually, I want to point this out because in this crowd, it's important to point this out. Even as far as I know, even for Eisenstein series, non-principal Eisenstein series induced from other parabolics, as far as I know, there is no geometric construction of the functional equation for these Eisenstein series coming from Drinfeld compactifications. Maybe Dennis can correct me or Sasha, but as far as I know, this is a big gap somehow in the geometric theory. The functional equation should be there, the Fourier transform should be there, but we just don't have it.
Okay, thanks.
You mean for arbitrary parabolics?
For arbitrary parabolics.
I don't think it's known. No.
Yeah.
I don't think there's a good geometric way to do it.
Although the structure of the formula suggests that you have exactly the same thing as for SL2. But
I agree, yes, we don't know it.
Yeah.
I think it's closely related to the question that I asked Dennis during his talk, and he said, I think his reply was that was the easiest way to go mad or something like this. I don't remember the precise formulation, but I think it's a very closely related question.
Okay.
Yeah, sorry for going so much over time. I didn't realize.
Okay.
Maybe if you try to vary your local system, well, your automorphic shifts in families, the answer for periods could become easier in some cases, maybe, if you try to formulate in families.
Well, one question is what, yeah, so one
like Rankin-Selberg, for example.
What is it? What is a family there?
I mean, well,
you mean because
if you admit Langland's correspondence, say for D models or something like this.
Yeah, one thing is whether you can use the degeneration of your spherical variety to prove something, but anyway, that's very speculative.
I mean, your adjoint representations appear just as a tangent space, right?
I apologize. Let us announce a 5 minutes break, but you are welcome to continue discussing during the break. And we reconvene in 5 minutes.
Thank you.
Yiannis, since this is an informal discussion, can I ask you a question? I already asked you before, but maybe you have some new comments about this. So is it possible? I mean, I'm just trying to package this in my head. So what's the relationship from the geometric point of view? What's the relationship between local statements and global statements?
Yeah, so maybe, so you're referring to local statements that say that under local geometric Langlands, here is the dual of.
Well, or even something simple like that. I mean, you had this. You formulate your one of your main conjectures about the sequence of categories. So suppose that, for example, you have that, and you want to go from that to something about periods, which would be global statements. So somehow, in what way are they kind of? Is there a kind of an implication in any direction? Or?
No, there is no implication in any direction. There is no implication in any direction. But as David Bensby has told me, that you can formulate a conjecture that encompasses all of them in a natural way, but the local conjecture will not imply the global one, and the global one will not imply the local one, at least at the full level.
So I mean, you have some kind of beta conjecture which implies both.
Maybe it's a little bit tautological, so we have a nice way to package both. I wouldn't say that there is a single conjecture that implies both. So David's idea is that this is some kind of boundary theory, boundary conditions for topological field theory, and somehow these boundary conditions should satisfy a lot of compatibilities, and all these compatibilities translate to various conjectures, but I cannot tell you that one of them implies all of them.
But the local conjecture has a factorizable form, and the factorizable form of the local conjecture, it doesn't determine the global one, but determines it up to a fairly small ambiguity. So it's a very, very strong constraint.
The factorizable form, I can understand that it has a factorizable form, but I'm saying that if you, so you're saying that the factorizable form does not yet imply the global one, but
I think it implies it's something up, like say in the unramified case, it determines, say, the sheaf that you get in the global conjecture up to something like tensoring by a local system. Okay. So it's weaker than, so the coherent sheaf on the stack of local systems is determined up to something like tensoring by a local system on the stack of local systems. So it's pretty.
Local system, you mean a vector bundle, or what do you mean by local?
Vector bundle with a flat connection on loc. So it determines, it's a fairly strong constraint on this coherent sheaf. So I mean, if it's a simply connected space, and essentially it determines it uniquely.
Okay.
Yiannis, can I ask you, so for example, in the cases of, well, in the case that I understand, for say for Wells-Purger periods for GL2, so somehow the square appears because H1 of your local system has a symmetric form, and what you really get is somehow a motif with respect to orthogonal group, which is not simply connected, I think, and somehow you should get groups which are simply connected at the material level. Is it something like this in other cases where you have square instead of usual L function? Square of period instead of usual period?
I don't know if simply connected is...
Well, what I mean is that your H1 of XE is orthogonal vector space, and you get a torsor under SO, but not under spin. And
yes.
Your square root of central value of the function appears as a lifting of this torsor to a spin torsor.
Yes, so this is a general idea that morally should be true, that somehow the square root should correspond to a lift to the spin group, but we don't know how to produce this lift at this point.
And it is the case in the Ishina case. I mean, Prasad conjecture.
Yeah, again, over there, we don't know how to lift to the spin group. So,
but do you get the torsor under orthogonal group?
I think so, because you have a symplectic representation, and then the H1 will be orthogonal, right?
Mm-hmm. Okay.
Sorry, Akshay, I'm muting myself.
Akshay, before you start, I have a question. May I share the slides you sent to me?
Yeah. Can you hear me?
Yes. So I'm sharing, and I will present you.
Okay.
All right. So our last speaker for today is Akshay Venkatesh from the Institute for Advanced Study. He will tell us about infinite sums of L functions.
Okay, thank you very much, Dima. Can you guys see me? Because I can't see myself.
Yes, we can see you.
Okay, I can't see myself. Tell me if it's strange. Okay. Yeah, it's a real honor for me to talk at Bernstein's conference. I think Joseph has been one of my mathematical heroes since I was a graduate student. And I was fortunate in my career, and I'm sorry there's a lawnmower outside, which tell me if it gets too annoying. I don't know what I can do about it, but it's fortunate that I got the chance to interact mathematically with Joseph. And what I'll tell you about is some things coming out of that I'm still thinking about. So about 10, 15 years ago, and Yiannis referred to this term that we spent in New York, Joseph and Andrei Reznikov were working on the analytic theory of L functions. And I think maybe this is a part of Joseph's work that is not known in the representation theory community, but it was very beautiful and influential, I think, in analytic number theory. So that, there's this question of bounding the size of L functions, which has various applications. And I was thinking about it, Joseph and Andre were thinking about it, and I think all of us encountered during our work some curious features of certain infinite sums of L functions. So I'm going to tell you a bit about the story in the first part of my talk. So my talk has a few parts that are loosely connected. In the second part of the talk, I will say something about this relative Langlands duality. In fact, Yiannis has just explained it, so maybe I'll give a slightly different point of view. And then the third part, I want to come back and sort of express my hope that this relative Langlands duality will shed light on some of these features, these phenomena involving infinite sums of L functions, which we saw in part one. Okay, so we're not there yet. I don't have anything very solid to say, but I think that's a reasonable hope for the future. And I should say that it's a large audience with varied backgrounds, so I have suppressed a lot of technical and even not so technical details in this talk. So if you want to know the detailed version of the statement, please ask for email. Okay, sorry, the lawnmower is 3 feet from me. So, can you guys still hear me okay?
Yeah.
Can you hear me? Yeah.
Yes.
Okay. Okay, so let's get started. So there's a paradigm in the analytic theory of L functions, and I think it was used very successfully in Deligne's proof of the Bay conjectures, that to understand the analytic properties of a single L function, perhaps to understand how large it is, instead of examining this L function in isolation, you consider a sum over a family of L functions. So the notation here, you think of this phi as something like a modular form, S is a complex number. And so to analyze a single value, you sum over some family of automorphic forms of value. And typically this sum you analyze by means of the trace formula. Okay, so this has become a very successful paradigm in analytic number theory. Typically, when you use the trace formula, the analysis is very complicated. But from the point of view of analysis, you just want to understand what is big, what is small, and so there are hundreds of papers that have followed in this general spirit. Now, sometimes if you look at these computations, you see that they have a kind of unexpectedly pleasant structure to them. That is something that you shouldn't expect, or I wouldn't have expected based on what I know about L functions, the trace formula. And that suggests there's some structure to these infinite sums that we don't fully understand. Okay, so let me give you an example. So in 1989, Kuznetsov, he was motivated by a purely analytic problem. He was analyzing the 8th moment of the Riemann zeta function. So they're not even anything to do with modular forms, Riemann zeta function. And in the course of that, he discovered something very interesting. He looked at this sum. The sum is over modular forms for GL2. And he takes the L function, the modular form, and he evaluates it at 4 points, Z1, Z2, Z3, Z4, takes the product. And what he found was when you sum this over modular forms for GL2, that sum has a symmetry that is not manifest that is not present for the individual terms. Okay, so there's some technical, kind of things I'm suppressing is if you were doing this for GL2 over Q, the sum would be infinite. So you need a weight function and so on. So let me not go into that. What Kuznetsov discovered is that this sum is symmetric under the substitution where you sort of flip all the zi's simultaneously. So each individual term has symmetries coming from the functional equation. But this is some global symmetry of the entire summation. And okay, so that's something very striking. There are other examples in the literature, but maybe this is one of the nicest ones. And so, you know, in the course of our work, Philippe Michel and I, and also Bernstein and Reznikov, gave kind of more transparent, I think, arguments for this formula, because Kuznetsov's original argument went through the trace formula. It's sort of not so clear how it happens. And so I'm going to follow, in particular, Andrei Reznikov really clarified what the representation theory principles are behind this type of thing. So I'm going to describe that basically following Andrei's ideas. And I'll describe it in the context of representation theory first. I thought maybe that's closer to the center of gravity of this audience. So first I'll say some stuff in pure representation theory, and then I will switch to automorphic forms and tell you the parallel story. Okay, so for the next few slides, we'll do representation theory, and in fact, just representations of compact groups. So here's a fairly elementary question. I take irreducible representations of SU2. So a V sub n is the n-dimensional irreducible, and I just fix a model for it, so symmetric n minus first power of the standard representation. Suppose I want to compute the invariance on a tensor product of 4 of those guys. And when I say compute it, let's say I'd like to have, this is some vector space. Maybe I'd like to have a basis, some concrete basis for that vector space. Okay, so this is it's a classical kind of question. It's fairly straightforward to answer. You can do it by sort of doing it in stages. So you first tensor the first 2 terms, VA and VB, and then you get a sum of irreducible representations. Their weights are indexed by an interval. You can tensor the second 2 terms. You get the same, again, a sum of irreducible representations whose weights are indexed by an interval. And then when you tensor those and take invariance, what you get is 1 dimension for each overlap of those 2 intervals. Okay, let me just write that more formally. So in this notation, x bracket y means hums from the vector space x to the vector space y. So this just writes out what I said. You decompose VA tensor VB. I guess, sorry, I'm pointing at my screen. I should highlight. Can you guys see it if I highlight?
Yes, we see.
Yes. Yes. Okay. Yeah. Okay. So I decompose VA tensor to VB. I decompose VC tensor VD, and each of these multiplicity spaces, each of these things you see in angle brackets, they're all at most 1-dimensional. Okay. And then when you tensor the A, B, and CD together and take invariance, you get a splitting of the space indexed by these irreducibles, E. You split it into lines. Okay, so that's pretty cool. Let's be a bit sloppy and say that's as good as a basis. So there's still some ambiguity of rescaling, but you could, if you pin down a way to normalize it, you get a real basis. Okay, so you get a basis indexed by an interval E. But this is not the only thing you could have done. You could have done these things in a different order. So I could have instead paired the first and third terms and the second and fourth terms. Okay, which is what you see here. So exactly the same as above, but I split it into pairs in a different way. And if you think about it for a moment, this is not going to be the same basis. In fact, it's indexed by an interval, but it's not even the same interval. The intervals have the same length, but they're not the same integers. And as you can imagine, this is a very classical question. You can write down explicitly the transition matrix between these 2 bases. It's a classical thing called the Wigner 6J symbol. It was already studied by Wigner in the 1940s. Anyway, the point is that you really compute this vector space in 2 essentially different ways. So you get an isomorphism between one sum of lines, one sum of multiplicity lines, and another sum of multiplicity lines. And it's a kind of non-obvious, it's an interesting isomorphism. Okay, so I'm going to, let me just comment now that all the things I just said will have an analog in the theory of automorphic forms. So I will just, in a few slides, I'll repeat this reasoning in automorphic forms, where you had these one-dimensional multiplicity lines, there will be L functions. Where you had an isomorphism of a sum of lines, there will be an equality of sums of L functions. Okay, so we're going to, that will be where we get this Kuznetsov formula from. But let me keep going with the representation theory for a little bit longer. So again, follows Andre's analysis of this. I want to really explicate why this worked, and by why were we able to get a basis in this way. And abstractly, what we did is we restricted from SU2 to the fourth to SU2 in stages, and we did it by passing through this intermediate subgroup SU2 squared. Now there were different choices for that SU2 squared, but maybe the first diagonal in the 1, 2 coordinates and the diagonal in the 3, 4 coordinates. The key point was what made this functional is that both steps of this restriction have multiplicity 1 branching. Okay, so that is when we take an irreducible of the big group and restrict it to the small group, it splits into sort of non-isomorphic constituents. If that wasn't the case, then this process we did wouldn't have split my space down into one-dimensional spaces. I would have just gotten it as some splitting, but wouldn't result all the way down to one dimension. So this principle, this general principle can be, of course, applied in other contexts. It's a, again, old idea. You can understand a complicated restriction problem by breaking it up into things, each of which have multiplicity 1. So let me just mention a couple of instances. I think the most classical incarnation of this idea is due to Gelfand and Cetlin. So in 1950, so if you take an irreducible representation of the unitary group, they wrote down a basis. They wrote down a basis for the representation where they could write down how all the elements in the Lie algebra act. And the point is that in this case, each of the multiplicities, when you restrict from a compact unitary group to one that's 1 smaller, it is multiplicity free. So what you can do is you can take your irreducible, you restrict it to UN minus 1, it splits into distinct things. You restrict it further, each one splits into distinct things. And so you get this tree-like structure with one-dimensional vector spaces at the bottom. Okay, so let me just write that formally for whatever it's worth. Your irreducible V is a direct sum. It's indexed by collections of irreducibles of smaller unitary groups. And then each one contributes a line. Okay, well, either a line or 0. And there's some interlacing property to tell you when you get a line. So this was used by Gelfand and Cetlin. It's very beautiful to give you a basis for an irreducible representation. And you can apply this principle, as you can imagine, in other contexts. I mean, the limiting factor is that there aren't so many multiplicity 1 branching problems around. But let me mention this easy variant, just because we'll encounter it later. You can restrict, Gelfand and Cetlin restricted from the unitary group to the trivial group, but you could restrict it to a torus just by taking the same chain as in Gelfand and Cetlin and padding at each stage with the torus. So I've showed you what it looks like for U3. And this way you can understand the restriction from unitary group to torus. Okay, so I'm going to go to automorphic forms. Are there any questions at this point? Okay. So what I want to do, I've told you some again, very old ideas in representation theory. I'm just going to re-implement them in the language of automorphic forms. So rather than give details, I'll just say how the analogy works, and then you can more or less see for yourself figure out for yourself how to say the same words in automorphic language. So for the rest of the talk, G will be a reductive group over a local field. You can think of GLN over Q. And the notation G sub F will refer to its points over a local field. Okay, so G is some algebraic object. G sub F is a topological group. You can talk about its representations of G sub F and so on. And an automorphic form for G, I remind you, it's a function on the locally symmetric space attached to G. which is an eigenfunction of some naturally defined operators, like the operators and differential operators. Okay, well, so whatever it is a function that has some extra properties on the locally symmetric space of G. Now, suppose I have a subgroup H inside G. I can restrict an automorphic form for G from this sort of symmetric space for G to that for H. Let's assume H is also a reductive subgroup for this discussion. And this will be, sorry, there's the Lorne mark here. This, when I do this restriction, it gives you a function, but it's no longer an eigenfunction. There's no reason to expect that when you restrict an eigenfunction of some differential operator, something smaller, that it should be an eigenfunction of any differential operator on the smaller space. So what you can do is you can take that restriction and you can decompose it into automorphic form. So you restrict the automorphic form in the big space, small one, and it breaks up as a sum of eigenfunctions. Now, okay, here's one of these details that I'm glossing over. You know, to reasonably define the coefficients here, a priori, if you have an eigenfunction, it's defined by its eigenvalues only up to scaling. You can't really distinguish it from its multiples. So you need to have some way of normalizing. So I'm assuming that we have some reasonable way of normalizing forms so that we can talk about the coefficients. So this is kind of an automorphic branching problem. Take an automorphic form, restrict it, and split it up. And it turns out this is very analogous to the representation theory of branching problem and representation theory. You can take an irreducible representation of the big group, you can restrict it to the small group, and it will split into irreducibles. Okay, in general, there may be some continuous spectrum here, but I'm ignoring that for the exposition. It will split into some irreducibles, each with some multiplicity. So this multiplicity is canonically a vector space. Okay, so you should think of these m sub i's that appear for the automorphic form as being analogous. They're numbers that are analogous to these vector spaces, the multiplicity spaces. Okay, so for example, if you think about the coefficient of the trivial automorphic form in the sum above, that's analogous to the coefficient of the trivial representation in the decomposition problem. That is, taking invariance on a representation, taking invariance for the small group on a representation. The big group is analogous to taking an automorphic form on the big group and integrating it over the small group.
I have a question. Are you, in your normalization, do you do it so that the MI are integers?
No. The MI are numbers. So imagine this is something, maybe they've been normalized to have first Fourier coefficient 1 or something like that, and then the MIs are some transcendental numbers. Thank you. Okay, now, you know, as far as we understand, as far as I know, this kind of branching problem in general, it's very hard to imagine a general good answer to it. Okay, it has kind of fairly chaotic behavior. There is, however, one class of such problems which have been extensively studied and where the behavior is sort of very pretty, which is the case of multiplicity 1 branching. Okay, that is where all these multiplicity spaces are one-dimensional. And extensive experience in number theory suggests that whenever that happens, whenever these multiplicity spaces are one-dimensional, these sort of branching coefficients above are also arithmetically meaningful. Namely, either they or their squares are values of L functions at some specific point. Okay, that's an empirical expectation that's borne out by many, many examples. So when the branching is kind of representation theoretically nice, then the numerical version for automorphic forms, those coefficients are nice. So with this dictionary in mind, you can now go and you can just take what I said about SU2 and re-implement it for automorphic forms, and you will arrive at this Kuznetsov formula. So let me just talk you through that briefly. I said for SU2, you take 4 representations, tensor them, and take invariance. According to this dictionary, what you can do instead is let's replace SU2 by GL2. We take 4 automorphic forms, you multiply them and you integrate over the diagonal. Okay, so you take 4 automorphic forms on GL2, P1, P2, P3, P4. You multiply them, integrate them over the diagonal, and you can analyze that in 2 different ways corresponding to these 2 chains, these 2 intermediate subgroups that you can put with these multiplicity 1 branching chains. And you will get 2 different expressions for that product. And if you take these phi1 to phi4 to be Eisenstein series, then you will recover this formula of Kuznetsov. Okay, modulo the non-trivial matter of regularizing everything. This making this converge is not entirely simple. But this is certainly philosophically absolutely correct. So this point of view, it was stressed by Andre, as I said. It's a general observation that whenever you can link from H to G by multiplicity 1 chain, that is a chain of subgroups such that restriction from each one to the next is multiplicity 1, has multiplicity 1 branching, then you can often express this period, the integral of an automorphic form on G over the space for H as a sum of L functions. Okay, and if you have 2 periods, you get, if you have 2 different chains, 2 of these multiplicity 1 chains, you get an equality between 2 infinite sums of L functions. Okay, so this was the point of view that Andre kind of advanced to explain these phenomena that we had seen in analytic number theory. And from some point of view, it's very satisfactory. On the other hand, there was a couple of things which I'm worried about ever since. The first is if you have an equality between one sum of L functions and another sum of L functions, you would like to be able to see it on the Galois side. That is to say, here it's being explained as some sort of slight fluke involving tricks with Lie groups. You would like to have some more direct explanation as to why it exists. And secondly, again, if you look in this literature where people have studied families of L functions, there are examples where you see this unexpectedly nice structure where at least I was not able to find such chains. So there's definitely reason to believe that there's a rigidity to this that goes beyond what is explained by this branching phenomenon. Okay, so I'm now going to go to the next part of my talk. I see there are some questions in the chat. Let me, okay.
I can repeat my question. I mean,
yeah, okay, very good, very good.
Asking everyone. So the question is that somehow when I say multiplicity 1, you're going to attach 2 meanings to this. You're going to talk about multiplicity 1 for representations of algebraic groups, for like fine dimensional algebraic groups, and for automorphic forms. Is there some kind of a priori relation between these 2?
Yeah, so let's take multiplicity 1 to mean, you know what, let me just answer your question in a couple of slides when I come to spherical brackets, or say something about it. Yeah, the multiplicity 1 at the level of representations is sort of slightly stronger than its algebraic analog. It's a more stringent condition. Are there any other questions? Because I seem to be doing okay for time.
Is this metaphor somehow related to Witten and others? Physics?
Oh, no, well, I think this is an old, like, it's been understood for a long, it's just a parallel behavior of local Lagrange and global Lagrange. And I'll say a little bit more about it, but it's certainly not, I think people have known this for a very long time. I don't know who to attribute it to. Are there any other questions?
Can I make a comment? I would say that you want to understand the function just of restriction from ban G to ban H as a after Lagrange duality just given by some kernel on product log cis H check times log cis G check, right?
That's yes, equivalent to. I would like to understand. Yeah, right, on the dual side, exactly.
Okay.
But the answer, we don't always expect it to be meaningful. And one of the things I don't think we understand in this story is where can we expect a reasonable answer to that? Okay, so let me continue. I'm going to talk now about relative Langlands duality. I will overlap with what Yiannis said. So I'm going to use this sort of metaphor of the Langlands program as being like a TQFT, topological quantum field theory. And I basically know nothing about topological quantum field theory, but David Bensby has convinced me that even knowing nothing, this is sort of a helpful point of view. It's not so much for proving things or doing detailed computations, but just for structuring in our mind all the different levels of what is going on and how they relate to one another. Okay, so just take this as a metaphor. It's not meant to be a mathematically precise statement, but it will help me sort of describe the different levels at which this story, different parallel levels where there's a story. Okay, so first, the overall picture of a TQFT is it assigns the manifolds of, we start off as the dimension, the manifold goes down, it assigns invariants of increasing categorical complexity. So let me first just describe how the normal Langlands fits into that hierarchy, and then the same for relative Langlands, whatever that is. Okay, so in the Langlands program, we study several things. And let's imagine we've fixed this reductive group, G, maybe G is GLN or something. So the global Langlands program, we can think of the, let's say we're studying automorphic forms over Z. Now, Z is the integers, from the cohomological point of view, it's an open three manifold. It's a Tal cohomology behaves like that. So we think of it as being three-dimensional. And what we study in the Langlands program is the vector space of automorphic functions. These are functions on the this arithmetic quotient associated to G. Now, of course, we study this vector space together with the action of Hecke symmetries and differential operators. But everything that we do lives in that vector space. Okay. Now, there are two, that's the three-dimensional object. There are two different two-dimensional objects that are traditionally studied in the Langlands program. That is, you could do the geometric version of global Langlands, and there you study a curve over an algebraically closed field, FP bar or C. And there, the object of study is not a vector space, but a category, the category of automorphic sheaves. The other two-dimensional object we study in the Langlands program is a local field. And there, the object of study is the category of representations of the group over that local field. Now, usually we think of local Langlands as asking to describe the irreducible representations of a group over a local field. But it's, I think, a reasonable enhancement to say we hope to describe the whole category. And finally, there's a one-dimensional thing, which I do not understand at all, but it's at least fits formally into this picture, which is that I understand that Dennis and Ed Frankel have explained to us that there's what geometric local Langlands should look like. So there you start with a geometric function field, like the field of Laurent series in one variable over C. And there the object of study is a two category. It's a two category of categorical representations of that. So the feature you should pay attention to is as we go down in dimension, the categorical level increases. Moreover, in a TQFT, it's not just about closed manifolds, but also about manifolds with boundary. So for example, in this, if you have a manifold and then another manifold that bounds it, so the manifold, maybe this original manifold, if it's assigned a vector space, the bounding manifold should give you a vector in that vector space. If the original manifold was assigned a category, it would give you an object in that category. And to the extent that it makes you can sort of reasonably, you have to use your imagination a little bit, but you can see the same structures here. Okay, so for example, this ring of integers is not really a closed three manifold, it's an open three manifold, and its boundary you should think of as being the real numbers. And correspondingly, the vector space that you see at the top row, it's not just a vector space, it's an object in the category of G of R representations. Okay, so it's kind of, you should think of this as this three-dimensional manifold is bounded by a two-dimensional one, and correspondingly, this actually lives as an object. Now, so what do we hope to do in the Langlands program? Speaking at this, very very vague generalities, is that we hope to describe all that appears here in terms of a kind of dual table involving the Langlands dual group. Okay, we hope to understand this vector space of automorphic functions together with this Hecke structure in terms of some similarly defined vector space involving the dual group, and so on all of the way down. Okay, so this is just a summary of the things we study in the Langlands program. I haven't said what the answers are in terms of dual group. I just said this is what we study.
Can I ask a question?
Yes.
So in this picture, it looks like you can't go to the dimension to increase the dimension arbitrarily, because then you will have to go too much down in the categorical line.
That's right.
The way it's supposed to be.
Yeah, it's a four-dimensional theory. So you could hope for a four manifold to be assigned a number, and for example, you can think of the trace formulas, the relative trace formula, as being in some sense filling that entry of the table, but you can't go beyond that.
But do you have a candidate for the value of a point?
Oh no. Yeah, I don't even know what a two category is. So sorry, I've already gone beyond my abilities when we hit the bottom row here. Okay, now this is what the Langlands program studies. Now, what is relative Langlands program? Actually, the word relative comes from Jacquet called it, so the relative trace formula, a lot of the study of periods was kind of put on a firm footing by Hervé Jacquet, and he called the corresponding trace formula the relative trace formula. It's a study of the Langlands program, a group relative to another piece of data, and that piece of data can be, for our purposes, described as a variety with a G action. So remember, this G was an algebraic group, and now I gave an algebraic variety with an action of that group. This algebraic variety, it induces an extra it gives you extra data at each level of that table that I did on the previous slide. Okay, so let me talk through two of the rows, and then I'll say, so on the previous slide, I talked about for local field F, I talked about the category of G representations. Now, that's just some disembodied representations of this topological group. But if you have something with Gx, it gives you a specific representation. Okay, if you have a G variety X, you can make a specific representation by taking functions on the points of this variety over the local field. Okay, now, of course, one has to be careful about functional analysis issues here, but essentially by linearizing X, you get a specific representation. So that is an object in that category. Similarly, in the vector space of automorphic form, so now we're talking at the top row, that's a vector space, but X gives you a specific element in this vector space, which is the Poincare series attached to X. Okay, so this was discussed in Yiannis's talk. I think he used the notation Px. He also used the term theta series. So there are some choices involved here, which I'm not discussing, but essentially giving an X variety gives you a specific automorphic form. The key ingredient in this automorphic form is you average over the integral points of X. So I call that the Poincare series. And this is a long-standing object of interest in number theory. One, because it produces examples, but more importantly, because in many examples, there's experimental phenomena that when the Poincare series is not an eigenfunction. It is not an eigenfunction of the Hecke operators. You can decompose it into eigenfunctions. And what are called the periods attached to X, the multiplicities, the coefficients, when you decompose this Px into automorphic forms, are sometimes, for suitable choice of G and X, are sometimes L functions. And this is the theory of periods in number theory. It's like, when is this an L function? How can we find out which L function? How do we prove it? And so on. So the overall picture, though, in terms of the diagram, is that each level of the diagram, X induces an extra data and induces extra data. And from the PQFT point of view, it is the same data that you would get by choosing a bounding manifold. Okay, so if you think of this local field F as being two-dimensional, it has a category attached to it. Choosing a bounding manifold would give you a specific object in the category. That's what X gives you. Same, so for the global field, X gives you a specific vector. So when it, so let me draw this diagram. In each of in the vector space that I described before, we now have a specific vector. In the categories that I had before, you have a specific object. And in this two category of categorical representations, you have a specific categorical representation. So my understanding is that this is called a boundary condition in field theory, but I'm afraid I'm not even sure I used the term entirely correctly. But it does, so the reason I've gone to this metaphor is just to try to put in your mind that there's some parallel. X induces extra data of similar nature at each level of the table. Okay, and if you take X, the special case where you take X to be G mod H, then you will, if you, what you see in this table will recover some of the things that we studied in part 1. Okay, on the third row, when you study functions on G mod H, it's related to taking H invariant on G representations. The first row is related to integrating automorphic forms for G over the subspace corresponding to H. Okay, I won't write that out because it'll take us too long, but what we saw, the parallel that we used in part 1, I said some stuff in representation theory and said that there's a parallel story in automorphic forms. It's really the parallel between rows 1 and rows 3 of this enhanced table. Okay, so now I'm ready to get to the point. Are there any questions up to here?
I have this. So the last thing you mentioned, I didn't quite understand. So in part 1 of your talk, you talked about restrictions of representations of finite dimensional representations of algebraic groups to subgroup.
Yeah.
But here in row 3, you talk about restrictions of representations of group over locally compact groups. So I don't see why on the representation theory side, there's a parallel.
Sorry, okay, the restriction problem. So really to do the restriction problem, I should take the X to be, I have two groups, G and H, and I take X to be G times H modulo H. When I decompose functions on that as a G times H representation, it gives you pairs of representations, one for G, one for H, where the H thing occurs in the restriction of the G thing. Does that make more sense?
Yeah, no, that is okay. So my question was about, so one paradigm is finite dimensional representations of algebraic groups. And the other paradigm
sorry, Dennis. No, you're absolutely right. And I just talked about compact groups there, so it would be as accessible as possible. I should have been, but let's think of those compact groups as being real, take the F to be R, okay? So think of them as real points, and we're thinking so I'm not thinking of, in the first part, don't think of it as finite algebraic representations, think of it as ordinary representations of compact real groups.
I see. And so kind of when you say H and G and H have multiplicity 1, if this multiplicity 1 occurs also for representation, let's say, of p-adic groups.
Yes, okay, that was Sasha's question, and let me say it now. Okay, so we do not expect, just as in the first part, so okay, here we have, at each level, we have this extra data induced by X. And now we can ask, if we can describe, assuming we understand how to describe the vector spaces and categories on the dual side, can we also describe this data induced by X on the dual side? And maybe don't expect is too strong, but certainly to my knowledge, there's no evidence that we could get some sort of nice description in general, okay, for any G variety. where the situation, or at least where we understand the situation to be good, is the multiplicity one case. And now, so let's, for the purpose of this talk, let's understand that to mean that functions on X of F are multiplicity one as a GF representation for all local fields. Okay, so that's just an ugly way. We can say that in a nicer way, as saying X is a spherical G variety plus some other conditions, but let's just assume it's sort of this, in other words, let's assume this third row is always multiplicity one over all local fields. So in that case, it is the belief of number theorists that at least the top row, which they have extensive experience with, also has a very nice description in terms of L functions. And more broadly, it's reasonable.
I'm sorry, just to relate it to L functions, you also need this normalization issues that you mentioned. How serious is this issue? Is this something mild? Or is this something really serious?
Well, so as Yiannis says, at the numerical level, you can use an L2 normalization, and that gives you basically a uniform conjecture. That always involves a square. If you want to take a square root, it becomes a subtle and I think serious issue. But if you're happy to work in the L2 world, then it's not an issue for that reason. You can do L2 normalization, and you square the period, and you normalize the automorphic form to have L2 norm 1. Okay. Are there any other questions? Okay, so now, as I said, we can hope for something in the multiplicity one case. So let me now say what has been seen already in Yiannis's talk, but with David and Yiannis, what we give in this multiplicity one case. So we we phrase this in terms of spherical varieties. It uses, and this is using the work of Yiannis and Jonathan Wang. We give a recipe. So actually, we give, starting with this G space X, we give a recipe for a space X dual under the dual group. And we expect that this X dual controls the answers to those questions on the dual side at each level of the table. Okay, we understand, at least I understand this best at the top level, but the expectation would be as a parallel description on each row. Now here I've said something a little bit egregious. Our recipe describes the cotangent bundle of X dual. Okay, that this T star X should be X dual. Our recipe describes the cotangent bundle of X dual. In many cases, there is a preferred way to polarize it. So I hope you'll forgive, I'm just gonna ignore that for the rest of this talk. But not always, but just for what I want to say in this talk, I prefer to suppress this and pretend we have access to this X dual, which we do not in general. Okay, so for example, let me just give you a sense. I say that X dual controls the answer at each level of the table. And we certainly don't understand everything, but we understand in several situations what that looks like. For example, at the top row, I said that you can take this period, you take the Poincare series attached to X and you pair it with an automorphic form. And now I want to describe for you what that looks like on the dual side. So I'll talk you through the general form of this. The automorphic form, phi sub g, gives you a Galois representation, a parameter, which is valued in the dual group. So the dual group acts on this dual space, and so you can take its fixed points, fixes some points, and let's assume those fixed points are discrete. Then we expect this period to be a sum of L functions indexed by the fixed points, and each fixed point gives a contribution that is the L function of the tangent space at that point. Okay, now coming back to Sasha's question, this is the form of the conjecture. This is it's assuming that you've fixed these normalization issues, which is not trivial in general. So this is not the most stable and robust version. But when you can normalize automorphic forms, for example, by using the Whittaker period, then this is what you would expect. The basic miracle, so this equation I just wrote, in specific cases, it's not new to number theorists. Like, it was understood that multiplicity one spaces correspond to L functions. The miracle for number theorists in this story is that this is an involution. Okay, this is an experimental, we have no proof of this, but you go from the space X to the space X dual. Now, X dual may not have multiplicity 1, and then our recipe doesn't apply. But when it does, and we can apply it again, in every instance that we have checked, it comes back to the original X. And this, at least for me, it's a very surprising thing, because it puts in pairing, there are many of these periods attached to various X that have been studied. And so this really says they come naturally in pairs. And Yiannis described some of those pairs, which I'll just write some here. For example, the Godemont-Jacquet integral is switched with a Rankin-Solberg integral, and so on. Okay, so many classical periods are paired with each other under this duality. Now, let me mention that, so the bottom layer of that is representations of this local geometric lines, this should be related to the conjectures that Sasha explained in his talk. Okay, so he stated, for example, a theorem of Sam Raskin about GM acting on A1. And in fact, this can be seen as a geometrization of Tate's thesis. Okay, so it has a kind of number theory context as well as a physics context. And speaking of physics, I should add so I know very little about this. I can only say the words for those who are more knowledgeable. In this metaphor that periods are like boundary conditions, I believe the physicists have long understood that duality acts on boundary conditions as well as field theories. And so the physical analog of the story is apparently the S-duality of boundary conditions, and it was studied by Gaiotto and Witten more than 10 years ago, in fact. So, well, I would like to understand more of that, but I don't. Okay, so I'm going to, I think, I have 10 more minutes. Is that right, Andre and Dima?
Absolutely.
Yes, no problem.
Take your time.
Okay, well, I have 10 minutes. I can stop for a question or two. I haven't been following the chat, but maybe if people can say if there's anything I can answer.
I think the chat lives, it's some kind of separate life. I mean, I don't think there are any questions.
Okay.
So actually, I have if you can go back to the previous slide.
Yes.
So again, the semantics. So one slide before that, you were talking about H. Now you have X, right?
Let's forget H. I just have X. That's better for me.
In terms of X, what does it mean to have multiplicity 1?
So let's take as a definition that for every local field, the functions on X of F are multiplicity 1 as a GF representation in the usual sort of think of smooth representations, smooth functions, and so on.
So if X is spherical, that would be enough for you, right?
I know it's strong. Yeah, it's stronger than spherical. Okay, so the basic counterexample is a spherical variety where the Borel orbit has finite stabilizers. So if you take GLN 1 ON, it's spherical for GLN, but it's not multiplicity 1 in this sense. And in fact, we do not understand, like it is, I sort of believe that example fits in this framework, but we don't understand what its dual is. So that's the sort of basic example of some spherical thing that falls out of this.
So these guys in the chat have been embarrassing me for my lack of knowledge, but so this presumes that you have a lot of fixed points, right, on X check.
Well, X check is typically, yeah, okay, good question. So X check is typically a vector space or a vector bundle over a homogeneous space, and the fixed points come from the zero section.
Gotcha. Okay.
Yeah.
Okay. Thank you.
Thank you. Actually, it's kind of amazing. We're all here. It's fantastic. Okay. So let me try to finish. Yeah.
Akshay, can I ask you a question as well?
Yeah.
So in the previous slide, can you say a few words about the duality between Godemont-Jacquet and Rankin-Solberg? Just quick comment.
I think I don't think I can say that in a short enough way to be helpful.
Okay.
So yeah, I'm sorry. It takes a while to explain, to unravel.
Okay, thank you.
Okay, so let's now, the last part of my talk, a little bit speculative. Okay, so I've tried to compute a few things last week for this, to give this talk, so I had to take it with maybe a pinch of salt, but okay, I think if you accept this duality, it leads you to something, I think, very interesting. So almost entirely the number theory study of periods has dealt with this multiplicity one case. And I think we have a lot of experience, and these cases are good. They have a nice theory. They're L functions. But according to our recipe, a multiplicity one thing may dualize to a space that doesn't have multiplicity one. Okay, and in that case, we can't define double dual. So it's not really clear what are these dual. And typically, or in many cases, the period defined by this dual space, it can represent an infinite sum of L functions. Okay, if you sort of write down the Poincare series for this in a perfect and automorphic form, in some cases, it gives you an infinite sum of L functions. And so I think, if you accept that multiplicity one periods are fundamental, I think we just have to accept that their duals are also fundamental. And so the resulting infinite sums of L functions are kind of meaningful objects that we should pay proper attention to. Okay, so there are a few examples, and at a sort of rough level, they all look they all show features similar to the one that I'm going to say. So let me just talk about one single example. It's an example that was mentioned by Yiannis, and it was the G, let's take to be SLN, and X will be the basic affine space. So the affine closure of this SLN modulo a unipotent. Okay, so this example, by the way, G doesn't have to be SLN for, there should be a version for this for all groups. It'll be clear that you can make sense of it for all groups, but the way to get, I only know how to get at it for SLN. This X is singular, and we want to replace it by a smooth stack. So I actually don't want to think of X as being G mod U. I want to think of it as being a smooth stack that I'll describe on the next slide. Okay, and that's important. Okay, because now if you plug this into our recipe, our recipe says in this case, well, the dual group is PGLN. The dual space should be PGLN modulo the torus T. Okay, so now this is not a multiplicity one space. It's very far from multiplicity one. But if you sort of just, so we don't really know what to expect here, but the prediction of duality would be that this formula that I wrote, that the X period, Poincare series for X in a product in automorphic form is indexed by, comes from L functions from X dual, and vice versa. You can switch in this the role of GX and G dual and X dual. Usually we think of G dual as being a complex group, but let's just think of it as being a group of split group over Q. This X dual you can think of as being a variety over Q. And then you get these two predictions. Okay. The first prediction, now this example it goes back to this very influential work of Braverman and Kajdan. The first of these equations is easy to verify. I'm sorry, I keep pointing at my screen thinking you can see, but the first one is very easy to verify. This PX is basically a normalized pseudo-Eisenstein series. The fixed points, there's a Wiles group worth of fixed points, but it's easy to check. The second is not proved, but I expect that you can establish something like this with suitable regularization. So more exactly, as we'll see on the next slide, both sides are kind of infinite sums of L functions, and one can see that the cuspidal parts of those sums match up. Okay, now something interesting and possibly anomalous will happen in the Eisenstein part. But so
fixed points here, I just forgot. Fixed points are just with respect to the torus, right?
Fixed points are respect with the Langlands parameter. So okay, this phi G. Let's look at this here. This phi G has a Langlands parameter. And so that Langlands parameter acts through the dual group on X.
Oh, I see.
In this case, it will only fix a point if it's conjugate to the torus, and that's why you only see Eisenstein series in that.
Okay, thank you.
But yes. Now, Now the second thing, let me just point out: this X is a stack in equation 3. X is now a stack, and so the fixed points that you get fixed points that have to do with representations of the acting group into stabilizers. So this sum, the first sum is a finite sum, but the second sum can be infinite. It's related to Langland's parameters going into the stabilizer groups of the stack. Okay, so let me now say a little bit more about the stack. I mean, this is something I'm sure people in geometric representations here know much better than I do. The SLN mod U parameterizes a flag in an n-dimensional space where each subspace is oriented. So oriented, I just mean it has an element, a non-zero element of its top exterior power. And I can sort of, the affine closure of that admits a map from a smooth stack where I just look at the sort of moduli space of things like this, but I allow the maps to become zero. Okay, so a line volume form, plane volume form, and so on, and some maps, but the maps can be zero. And this is, it's closely related to Lomon's compactification. It should also remind you of this Gelfand-Settlin story, and that's not an accident that that's going to be crucial for the computation that follows. So we would like to know, okay, so we're trying to understand whether the duality applies. There's in this case, where one of the spaces is not multiplicity one, we want to check then that this equality period is now an infinite sum of L functions. And the right-hand side, as I said, is a sum indexed by Langland's parameters going into various stabilizer groups, so it's an infinite sum. And what you can check is that the left-hand side has the same structure. The left-hand side amounts to integrating a form on PGLN over the torus, and you can compute it by using this multiplicity one chain that I described in the first part of the talk. Okay, you take the Gelfand-Settlin chain, you pad it with a torus. And okay, so now once you go past when n is 4 or higher, the divergences will be quite unpleasant. But what's at least true is the cuspidal contribution of that is exactly what you would expect. That is the cuspidal contribution, the sum, you get this sum over cusp forms on all, when you do this expansion, you get a sum over automorphic forms on all the intermediate groups. And the cuspidal contribution there is the same as what you see on the right-hand side. Eisenstein, I don't know, and my experience from doing other things is that there can be actually anomalous terms that arise. Okay, so that's analysis which has to be done. But at the very least, the prediction you get out of duality, I believe there'll be a true statement that is very much in that spirit. Okay, but it may require some serious regularization of Eisenstein part.
Do you know that it works for n equal to 2?
Yeah, for n equals 2, there's no problem. Yeah, n equals, yes. Well, okay, let me say, I haven't thought through that, but I'm pretty sure it should work. Yeah, numerically, there should be no problem. Oh, I'm sorry. Yeah, for n equals, sorry, for n equals 2, there's only one summand. So it's true trivially for n equals 2. I think even for n equals 3, n equals 3, there shouldn't be any convergence difficulty, but there may be some anomalous thing in the Eisenstein thing.
Just to calibrate, Akshay, when you say trivially, you mean Welsh-Berger formula? What do you mean by trivially?
Well, I was even getting with a split torus, so I mean Hecke's formula. Okay. So this formula in that case is just a very fancy way of saying Hecke's L function. Okay, so I'm almost done. I'm sorry. Okay, I'm 1 minute over time. This is my last slide. Just to summarize, so what we've seen here is that infinite sums of L functions arise, I think, naturally as sort of the duals of unique periods. Okay, so we believe in unique periods. I think we have to believe in their duals. There are many interesting examples to examine. I've showed you one. And I think, as I said, this powerful method to analyze these non-unique periods is this multiplicity one branching chains. And but I think to make progress, we really have to understand the phenomenon of part one, that when you have two different such chains, it gives you two different ways of computing. We need to understand how this plays with the duality. These you need to really understand the part one phenomenon in terms of duality. And I'm hopeful. I don't have anything useful to say, but I'm hopeful that can be done. And so remains only to say happy birthday to Joseph, and I wanted to thank you personally for, I think your mathematics has been a source of inspiration for me throughout my whole career. So it's really nice to give this talk in your honor. Thank you.
Thank you.
Thank you. Questions?
Can I ask a question, the following question? So somehow, from a certain point of view, at least part of what you were talking about was about this kind of subject of symplectic duality and so on. And so there, if you sort of try to really think about it from a physics point of view, then what happens that any kind of nice, let's say, symplectic DG stack or whatever, gives rise to some kind of field theory, and then you want to consider some kind of dual field theory. And the problem is typically dual field theory is impossible to describe. But sometimes it is also given by some kind of symplectic DG stack, and every time you have such a thing, you can formulate some kind of at least equivalence of categories. So I wonder if your condition of multiplicity 1 has something to do with this dual being also having some content description of.
Yeah, that makes a lot of sense. Like to the extent that it seems like physicists envision a much broader duality, and from that point of view, we're presumably cutting out a set of cases where the duals can be cleanly described.
Yeah, but I'm just trying to understand somehow where this multiplicity 1 condition is coming from, so to say. So I mean, I understand that technically it's a convenient condition to have, but somehow.
Yeah, I have no experimentally we know it works, but I don't have that. There are examples which is not quite multiplicity 1, where there's something. It's clearly not, because it's not stable under duality. It's clearly not. There's some larger nice class that contains it, but we don't know how to describe that class.
And so another question, so your last example, somehow this stack that replaced the affine closure of G mod U, it also somehow appeared in my talk. So I wonder if that's the same, so to say, type of invariance. So somehow.
Yeah. And by the way, it has this nice property that it's, that you can, if you take the characteristic function of ZP and you push it down, you get the basic function. So it's,
yeah, this is actually known in this case. It's not a completely trivial theorem, but this in this particular case, it's known, and somehow, well, at least in some categorical way, it appears in our paper with Finkelbeck and Kajima that even not a lot of functions, but a lot of sheaves that. That the claim is that somehow when you push it forward in some sense, you get the thing corresponding to the regular representation of GLN.
Right. Yeah, so I believe some of the things in your talk were kind of some incarnation of a Gelfand-Sedlin story, or could be seen that way mathematically.
Sure, absolutely, yes. But I wonder if that's kind of if there's just similar things, or whether that's a sort of the same thing. Okay.
Yeah, I have a question.
I think that if you take the local ramified conjecture that we are formulating and apply it to this Gelfand-Sedlin setting, then you might get a conjectural equivalence for, like, you might get the Langlands dual for the category of sheaves on G of F. And out of that, I think, if you can formulate this, maybe that implies your conjectures, Sasha. For example, your Whittaker category is morphisms from sheaves on G of F to Whittaker sheaves. So if you know the descriptions of both objects on the dual side, then that would spit out your conjecture.
Let me ask a basic question. So we have a sum of values of L functions. I assume that this yoga doesn't, that the special values are always essentially central points. Is that correct? That's one question.
No, I don't see that they would have to be, although in the examples, okay, I have to admit the examples that I thought of, it's all central points.
And it's not, I guess what I'm saying, it's not a statement for all S. There's some.
It is not. So Peter, I don't know the right term, but I will say all the examples I know are central points. So I yeah, at the moment, yes.
Is there some, so there's going to be, you're predicting some new sums that are meaningful.
Yes.
Central points. Is there something that I can fantasize about?
Well, I can't sort of say it here, but I can say some other examples of interesting periods whose duals look like this. And one of those is the doubling method. So PS and Rallis have a doubling method. On the dual side of that, you get something that looks like something, I think, an interesting period that looks like an infinite sum of L functions, which I can write down, but maybe not here.
Yeah, sounds very enticing. So. Because all these, as you pointed out in the beginning of your lecture, these formulae are very powerful analytically. And as I was said in the middle there, somewhere about positivity, maybe in Yiannis's talk, maybe that's not so well known to the other 203 or more listeners, that if you take a Dirichlet L function with a real quadratic character, if you could prove L1/2 chi is non-negative, it would change many, it would be dramatic, absolutely dramatic in the theory of Siegel zeros. So somehow we really, just understanding the non-negativity is extremely deep. And so these formulae which do produce that in some cases are very powerful. Yeah.
Yeah, I don't think there's any expectation of producing for a Dirichlet though, because the things that we have squares are always, as you know, of the other type, and then we don't see any exception to that.
Yeah, I don't expect that, but if you have some natural sums which are new sums of central values with some geometric meaning, I'm sure they would be powerful. Yeah.
I believe there will be many from this.
Okay. Thank you.
Can I ask you another question? So in some of these cases, not in all, but in some very limited cases, this kind of what you call relative Langlands duality also works in the quantum case, which sort of from the point of view of classical anthropomorphic form theory corresponds to doing something for covering groups. So the question, can you say?
So we have looked at, sorry, I don't know anything. I guess this quantum story has more than just covering group. Covering groups are some sort of special parameter, right? That's my understanding. So sure, I don't know.
Yes, but in number theory, you only have special parameters in some sense.
In only, and so yes, I'm afraid I can only give you answers by example, because our theory as written doesn't. But by examples, simple examples with covering groups appear to have duals that behave appropriately.
I mean, I only basically know this example that we started with Finkelberg, Ginsburg, Trafkin, where you have this JLN times JLN minus 1 quotient by JLN minus 1. So in that case, there's a quantum story, but I don't know where else do you have.
Okay. So I don't know if there's in number theory a metaplectic version of that, but so in number theory, there are periods on metaplectic groups, and at least the simple ones that we've looked at either appear to have a dual or they feel like they have a dual, but we can't quite figure out what it is because it has some stacky feature. But anyway, our recipes don't literally apply. So that involves some guesswork at that point.
More questions?
Thank you again.
Before we finish, we remind that tomorrow there will be 3 lectures, and after that we will have a group photo and a dinner. So you're all welcome very much to attend all these events.
What's the menu?
It's a free menu. You can order whatever you can get. Okay, thank you.
Thank you.
Okay, thanks.
Yes, well.
Yeah. Okay.
maybe the organizers could send the copies of the chat to everybody, because there are interesting questions.
Yeah.
Would be nice.
So, we'll get it, edit, and we'll send it.
Okay, thanks.
Thank you.
Is there an excursion for the conference?
What?
An excursion.
Virtual, easily. I can organize. I will think about it. Okay.
Will the recordings be available somewhere or not?
So the recordings are available on YouTube. So all this was happening live on YouTube, and then it stays on YouTube.
Thank you.
I guess one file for a day, but of course you can scroll it by time. And the link to YouTube is on the conference website. See you tomorrow.